used to record. Okay. Yeah. So yeah, obviously the DNNs are mostly used as classifiers for classifying some set of inputs into various classes. There is no now here you're learning an optimal strategy, or usually called a policy, which is a sequence of actions as opposed to just classifications. And the goal here is described as some property of dynamic behavior, evolving dynamic behavior. That is the goal of the outcome. So that is what is different in this case. To take an example, you have, so here is some grid world. The grid world is described, as shown here, has a number of grids. And the state of that world, which is the thing the agent controls, is called an environment. Here, there are two state variables, X and Y, which denote the position of the grid, the coordinates of the grid. And the goal here is the agent is there's an initial position for the agent, and the agent has to learn how to reach this lower left-hand corner marked blue, the most optimal way to get it. The actions that he's allowed to perform are move right, left, if the agent is at the edge, obviously, if he cannot go off the world, then he'll remain the same way as a result of taking a move action. And the same case, okay, the black portion here, the grids that are marked colored black are obstacles, and you can't move into it. So the goal of the agent is to figure out in each state what action he can perform. The optimal sequence of actions to reach the target. Okay. Now, additionally, one of the other inputs that reinforcement learning framework has is the environment gives the agent a reward as a result of performing the action. And these rewards are given is a function of state action pair. And that is something that has to be devised. That is the additional information in addition to the state and what actions can be performed that the agent can use. And these rewards, some are hints that to the agents, so to speak, about how good those actions, the local actions, are towards reaching the goal. That is an additional information that the agent has to learn the optimal policy to accomplish the goal. Okay. So put it in so this like a formalization of this of an RL framework, which shows the various components. As I said, there is an agent and there is an environment. Okay. Environment has states and actions. The agent is allowed to observe some partial information about the state of the environment, and he knows also about the actions which he has to choose. Okay. So there is a state space for the environment. There's an action which maps a state to state. And in each state, there is a set of actions that are considered to be enabled that the agent can choose from to perform. And as a result of performing that, the agent gets a reward function, which is a function of state and the action taken, which is can in general be a real valued number. And the goal of the learning objective is a policy that the agent has to learn what action is the most optimal to perform in each, there's a policy function, and the optimal policy is one which chooses a sequence of actions in the state to maximize that cumulative reward that he gets as the agent performs a sequence of actions. Okay. Any questions so far? Okay, so once again, these are the, the various components. You have the environment with state and thing, and the reward, designing an appropriate reward function is part of setting up the RL framework. And the policy is a sequence of actions, and that is what is being learned. And usually the workflow of thing is sometimes there is a training phase, just like for DNN, where you simulate the environment in a base in which you learn something. I mean, the more optimal policy, and after that, the learning phase, you can deploy it on a real life situation to do. So that's kind of the workflow of RL. So some little bit of mathematics about and the most popular learning method within the RL framework that is employed is what is called Q learning. And there's a small bit of a mathematical background that I'm giving you to initiate you into Q learning. So the problem of coming up with solving for the optimal policy can be formulated as an optimization problem within as a dynamic programming optimization problem. Here, the objective function is this one, okay? This which computes the cumulative expected reward, okay? And so given any state, for any state, and given a sequence of actions, you can accumulate the reward as a result of performing every action in that sequence. There is a discounting factor that is usually used to discount the future rewards. Okay, you can discount them give certain weightages, how much weightage you want to give for present versus future rewards, and that's what the gamma factor is, which is some fraction between 0 and 1. So the optimal expected reward for any given state can be defined as V star, which is overall possibly infinite sequences of actions. You have to it's a maximum expected reward of all sequences of actions that you could possibly take, starting from from S. And that's what, mathematically, technically, what reinforcement learning algorithms will have to compute. In the framework of dynamic programming, so there is this famous Bellman equation, which you can, it's a recursive equation, which kind of defines this V star function based on this optimality principle that no matter what action you take from the current state, as long as you make sure that from the successor state that you get as a result of performing the current action, you're always using optimal policy. Then you can express V star S recursively in this fashion. So what you do is, it has to be that you have to choose that action in the present state, which maximizes this sum. You get the current reward as a result of performing that action, and then you apply V star S discounted by gamma on the successor state. So any solution to this V star, which maximizes this, will be the ideal optimal policy. Now, the real big question is how to solve this Bellman equation, and Q learning which is what all the three papers that will be discussed today will be using, is one way. I mean, I will get to Q-learning in the next slide. So, but how, if you're able to somehow solve this Bellman equation, then you have a solution V star, which is the, gives the, action to take in the current state in order to, optimize your, get the best cumulative reward. Then you can then use that V star function to make a Q function, which will give a score for every state action pair, okay, which just adds the reward that that you get from the environment as a result of performing that action in the current state. And then from the next state, you can do those actions that fetch you as per V star. So then, in order to determine a policy, which is basically policy function, which you'll have to determine what the current action is, you could choose that action in the current state for which, that gives, the best Q star value, though that action which gives, among all the enabled actions in the current state, the largest score, the action corresponding to the largest score. So usually what is done is this Q function is what is synthesized, okay, by the Q learning process. And then based on the score, you could, you can use a softmax function or some normalization thing to compute the associate probability for each of the enabled actions in the current state. And you pick that one which has the best probability to accomplish that action, which can lead to the action that with the highest probability that can lead you towards the optimal solution. Because if the probability, all the actions are equally probable to be optimal, then you can pick one of the actions randomly. And or you can have a policy where you can always intersperse. In certain steps, you can pick the action randomly, or in other steps, you can pick an action which is determined by the optimal Q function, and you can mix these two things. And that is done in practice as well. Okay. So a little bit about how to solve this thing. Yeah, you can either, one way, of course, is the Bellman equation. In theory, this recursive function, you can expand it out, okay? And of course, if there's only, the state is finite and there are only finite sequence of actions, then maybe you can bound it by certain number, and then that is one way to do. Or in general, for infinite state, or even for finite states, and there are the traces can be infinite. In general, you will have to use certain analytical methods to solve this in the limit case. And there are analytical methods in literature to solve these things, both in the infinite case as well as finite cases, which give certain guarantee of convergence and so on, provided you are willing to settle for an optimal solution within a certain epsilon band. Okay. That is, So what I want to get here now is basically one slide, which gives you what Q learning is, which is a specific and popular method to solve the Bellman equation to come up with a Q function that is as close to optimal as you want. As I said, in general, I say MDP here, the environment is usually, I'm assuming, I didn't mention that here. So it is represented as a transition system, as I've already said that there is a T, okay, as this is an action is a transition step. If it is deterministic, you can, in general, allow the environment to perform non-deterministic action. This is the T that I was talking about, in which case, and each transition can be made probabilistic also. Then you, in general, the environment could be a Markov decision process. Okay, but yeah, that is immaterial to what the Q-learning method. So in Q-learning, it learns, it's a method in which Q star, the optimal Q star function, is learned adaptively from a history of interactions of the agent with the environment. Okay, let's suppose we represent Q function as just as a table indexed by state action pair. And since the state and action can be the domain can be huge, it's possibly you represent them as using some hashing thing. And we assume that it is initialized to some initial estimate. So in this Q-learning method, you start with an initial estimate of that, the Q star function, and you simulate the environment based on the interactions of performing actions on the environment. You learn, and then as you learn adaptively, you update the Q star, the Q table, to get iteratively better and better approximation to the optimal Q star. Okay, and that's what is done as follows. In each iteration, I, with the environment, say in state Si, you choose an action based on the current estimate of the Q table. You choose an action AI plus 1 in state Si, and then you perform that action, as a result of which you get a successor state and a reward. Okay, and then you update your Q table as per this formula. Okay, so there are various factors here. So the I plus 1 value, of the Q table, as a result of performing AI plus 1, is the current value plus these two factors. What you do is there is a reward function that you get as a result of performing this action, that you get from by simulation of the environment. And then there is a discounted optimal future reward that you can get from the next state. Okay, that is from Si plus 1. So you pick among all the actions that are enabled in the next state, you pick the maximum. That's the maximum future reward, because discounted, by something. And then you, and this is the error. What is inside this red parentheses is the error of the current estimate from the new value that you get, as a result of the new reward, that discounted reward that you get as a result of your choice of action based on the current table in the current state. And that is the error thing that you kind of learn. That is that you have learned. This is and that that error you update that's also taken into account as part of the value that you will update the current value by. Okay, so there is an alpha factor here as well. How much you do by how much weightage that you give for future reward, that you learn, as opposed to based on the reward that you get currently, which is the how much weightage you put for the learning factor. So both alpha and gamma are hyperparameters which are used to balance the future reward versus the current reward, and that's how you update the Q table. The Q table, and you keep doing it until in each step it gets you hopefully close a better estimate based on the action that you take in the current thing, and then you can run this iterative process until the Q table converges, the values in the Q table converge up to a certain a tolerance level. Or there are ways in which you could, I'm going to skip this thing because I'm running out of time and I don't want to eat into the thing. So, and that's how, so you can, as I've said here, there are two kinds of policies. You can either run offline versus online. An offline policy is you use that, Q learning phase. You keep learning, you keep updating the Q table, by performing, simulating the environment and updating the Q table until it, it converges. Okay, in doing that, you can do. There are things as to how many samples do you, how many steps, how frequently you update the table as get updated in every step, and usually that's not what's done. You run it for a certain number of steps called episode, after which you update the Q table for all the states that you get in the trace that you get out of simulation. And how you terminate, that is also a factor. That depends on what is the tolerance that you give for consecutive Q table values. And of course, as I've already said, you can use exploitation, decision based on the Q table, or exploration, which is pure random strategy. Finally, like I said, an offline strategy is where you have a separate training phase where you learn the Q table until convergence, and then you deploy it for in actual test case. Or in certain applications, it is, you can use the online version where you keep on updating the Q table until you accomplish your goal. So they're both offline as well as online strategy. Okay. Finally, I'm not going to go through this thing. You can also, there are techniques to where, I said that, one obvious way to represent this Q function is as a Q table with hashing functions to make it compact. Or there are schemes, where you can represent it as a neural network, a DNN. Okay, because after all, DNN can serve as a compact function approximator, and also they're good and they can work with continuous values. And then the updating of the Q table itself can use gradient descent methods, by where the loss function will be the error. The loss function will be the error that you compute between the current Q table values and the result of performing simulating the environment of a new function. So there are ways you can use DNNs to do it as well. And I leave it at that. I hope you got some overview of the reinforcement learning. So before I pass the baton to Bijian, are there any questions on my part of the overview thing? Okay. If not, then I will stop sharing.
Hi, just a small
question. Yeah. If there are no questions also, you can add comments, okay? So if anything that I have...
so just a small thing I wanted to ask is... No, I just wanted to ask this because I suspect it might come up in some of the presentations. The action, the result of the action as in the state that one goes to, and the reward that one gets when one chooses an action, both of these two distributions are Markovian, as in they don't really care about what happened in some previous state or some history of the play so far, right? So if we visit the same state again and again, no matter what path we took to visit it, as long as we choose a particular action, the distribution of reward will look the same, right?
Yes. Yeah.
Okay. Yeah. Sure.
That's right. But I think there is a way.
Because the main thing is because Q learning converges only if this assumption is true.
That is true.
Otherwise,
In Q learning, that is certainly the case. Okay, I know that there are people talk about certain Markovian rewards also by considering future successor states. Okay.
Okay. Sure.
That what you call as which do you consider as Markovian? I mean, I know
the one where there is no history. So this setting where the Q learning converges is, I think, typically called Markovian.
Yeah, this is Markovians. And the non-Markovian thing is where you look at past or
either the past or the future.
Or the future. Okay. Now I know that. I mean, one easy way I've seen some people extended it is okay. You compute a few look aheads. I mean, few then you can add that to
this. And or you can just if the history you're talking about is some finite state machine, then you can take a product of that and create some product MDP or something.
Yeah. So actually, Bayesian will be, for example, you brought out, okay, if you keep visiting the same state, you're not learning from those things. There are, here's a scheme that he will talk about. I think he will. Okay. We have, if you agree with me, Bayesian. So that is one of the things where you can keep account, okay, some additional information as to how many times you visit that state, okay?
Yeah.
As part of designing your reward function, or you can embed that in your, if you keep that as part of it, you make it observe. That is one way, okay?
Right. And as long as that is, as long as that is, I guess, as long as that's the only memory we're keeping track of, I think the convergence guarantees.
But you're right that they don't guarantee. The convergence is not necessarily guaranteed in those cases. But in the literature, I've seen I've seen lots of variations to this thing where they add some additional information.
I guess one can always simulate a non-Markovian thing as a Markovian thing if one allows infinitely many states. We'll just call it a new state.
Right? Correct.
But even in that case, I don't think we have convergence guarantees. Which I think will then, but people do RL on infinite MDPs all the time.
I think there is something like they if there is some bound on the additional information or something, they converge. I've seen these kinds of.
Yeah. Because then I think it'll come down to a finite thing.
Yeah.
Any
other comments or questions? You can add general comments. I know that some of you would have learned, from there is tons of literature information on the web where you could. Any other comments that you want to make? Okay.
A part of my paper is actually like converting it to doing it so that we know what states we have visited before, like how.
Oh, that's interesting.
Ganta said that we take a product MDP and then we keep track of what states we have visited.
Oh, does the shielding paper talk about that?
Yeah, I mean, we want to know what traits is feasible or not, and we do it using that, roughly. I'll talk about it.
So maybe then we can revisit that question in the context of your the shielding. I know it's a bit rushed, but
hello.
Yes. Any other comment?
Am I audible?
You are audible. As soon as I make you co-host, you're ready to go.
Okay.
Yeah, you can share.
Okay. Yeah. So I'm audible, right? Like properly?
You're audible, but we can't see your screen yet.
Yeah, that is fine. I'm sharing. Just like want to make sure that the audio is working fine.
No, your audio is fine. It's fine for me. For the rest of you also.
Okay. Yeah.
Yeah, sure. Yes.
I'll just.
what's happening?
Yeah, 1 minute. I'll just. Something happened and I just lost the tab that I had the presentation in. So yeah, 1 minute. Is my screen visible?
Yeah, you can see it now.
Okay.
It's visible now.
Okay, yeah, 1 minute. Yeah. So is it fine? Like everything?
Yeah, please go ahead.
Okay.
I think it's fine.
So yeah, so like I'm supposed to so like after this introduction on Sioux learning, I should this paper deals with how to apply this reinforcement learning technique to a problem on distribution testing. So I'm starting with describing what this problem of distributed system testing is, and after that I will mention the problem statement, and then I'll go to this agent environment setup, RL setup. Then briefly mention about the ideas of the different RL-based approaches, namely this neg RL, bonus max RL, and waypoint RL. This negative RL is part of Akash Lal's paper, and bonus max RL and waypoint RL is a recent work in Sunit's paper in the year 2000. I think it was published 2024. So yeah, and after that I'll just go through the experiments and conclude with remarks and similar works and references. So yeah, let me get started with the distribution testing, distributed system testing. So concurrent programs.
One of them, I think both these papers appear in OOPS, correct? Yeah. People are interested.
Yeah, I think so. Yeah, I think so. Second one is the Srinithi's paper is in OOPS definitely. That one is also in OOPS.
First one you don't, not sure. Yeah, okay.
I don't exactly remember because the website was Microsoft's website. So yeah. So concurrent programming is a technique where two or more processes start to run in an interleaved manner through context switch and complete in an overlapping time period by sharing the resources. So like this shared resources may be the memory, maybe different things. So multi-threaded programs with shared memories. Here the atomic actions are read and write with shared memories. Synchronization is done by locking of shared resources. So if there are two computers like accessing the same memory, then like a same resource, then at a time they lock the memory for one computer so that discrepancies doesn't happen. So that's a multi-threaded system. Distributed systems are like where no shared memories or acclamation. Memories are shared, but acclamations communicate with message passing. So action is triggered by a message. Synchronization is also done by message passing. Now, this controlled non-determinism occurs when more than one machine becomes enabled, and data non-determinism happens when the generated uncontrolled scalar values, example models for handling user-given input. Now, stateful techniques fully model the system state space, and explore the reachable states through explicit methods. Stateless techniques such as control concurrency testing dynamically control and explore the interleavings without modeling the full state space, aiming to enhance coverage by systematically testing different action schedules. So let's describe an example, a simple example.
Since you had another bullet, you didn't say anything. You said about stateful, stateless. Did you say?
Yeah, stateless such as control concurrency testing. Yeah, I said dynamically.
Okay.
Yeah.
Without action. Okay.
Yeah, without modeling the full state space, we in this way enhance the coverage by systematically testing the different action schedules. Now we come to this 3-worker example.
This approach that you're going to be describing, this RL1, would you put under stateful or stateless? It is
stateless, because like we are systematically testing the different action schedules, and we are not
Yeah,
modeling the full state machine.
Yeah, I think there is a little bit of, I mean, I can argue with it, but I'll raise this question later on after you describe it. So there are some people, I mean, it is neither stateful or stateless is what I think, but
I see.
Okay, so fine. Yeah, so
I see.
yeah, you can maintain the position that it is stateless, and I will raise that question later. Yeah.
Okay. Actually, I think in this wildcard example, I was not able to exactly describe it in the Trident. Today, I should like describe it properly. So
No. That's what dry run up for. Okay, go ahead.
no. Like, I just like told you. So yeah. So okay. So this so this there's a program between three workers: worker A, worker B, worker C. So two workers keep sending messages to the third worker C. Now, if A sends a message, it's denoted by 0. When B sends the message, it's denoted by 1. Now, C has a constant string eta, which is some length and some n-length string, and maintains a counter that is initialized to 0. So if the ith message, which is 0 when A sends it, it's denoted by 0 and 1 when B sends it. The ith message received by C matches the ith character of eta and is incremented. Otherwise, n is set to -1 and is never updated again. This is the setup clear?
Yeah. I mean, it's clear to me. Any questions? Yeah, you can go through.
Like in the audience okay. So the program reaches a bad configuration when n is equal to n. So like at the given n, if if there are exactly n number of increments after n message passings, then the program is in a bad configuration. So we test if the program reach a bad configuration. So note that for any string eta of length n, there is exactly one way of scheduling A and B that causes C to raise an error after n messages. Well, because like if it's any string, you just if the first letter is 0, you have to get the schedule from you'll have to get the message from A. If the second one is 1, then you'll have to get the message from B. And in such a manner, it's exactly one scheduling process between A and B that causes this error state after n messages. If the C starts with the n-length string. So the effectiveness of each scheduler is measured. So the effectiveness of each scheduler is measured by something as the B value, buggy value. It is defined as the percentage of buggy program runs in sufficiently large number of runs. So like so if you keep on testing it in many runs, like it's kind of putting a metric measure on the coverage. So like how many buggy programs we are encountering, because that's our motto, to find the buggy programs, to find the error states.
Yeah, I want to pause here to let the audience ask any questions, because I think this is the running example, and I think he will use it mostly. So any questions that people have about this particular example, as what its error state is, and how the effectiveness of the probability is measured as this probability. Any questions? Okay, we'll move on.
So in case of random scheduling, we schedule A and B randomly to the message C, whereby C keeps on getting a random string of length n up after n messages. So for any string eta of length n, the random scheduler has 1 of 2 by n chance of producing that buggy string, as it must choose between workers A and B exactly according to eta. Since there is only one, there are two to the power n many possible schedules and only one that leads to the buggy state. So a random scheduler gets the buggy state with the probability 1 by 2 power n. So although the random scheduler has similar B percentage probability values, buggy percentage value for the different strings, its effectiveness is poor due to the exponential dependence on the string length. It's like 1 by 2 power n. So it's like with very small probability to actually find the buggy state. So now the QA scheduler, which we shall discuss in which the paper describes, technically the previous paper of NewZoomLink4Class describes for the first time, that QA scheduler exposes the bug for each string with a much higher B percentage compared to the other schedulers. So this QL scheduler will find the buggy states with much higher probability and like that is like much greater coverage. So QL takes advantage from observing the state of the program, which the state of the program is a counter M during exploration and optimizes for coverage. For this problem, we set it up to observe just the value of the counter M of worker C as M is set to -1 on wrong scheduling choices, it is forced to learn scheduling decisions that keep incrementing M, which leads to the bug. So the main idea is to give a negative reward on the wrong scheduling choices, and we shall see in the Q-learning, and like as in the overview we saw, like the main point of the RL procedure is to increase the Q value. So giving this minus reward for getting the wrong schedules, it will try to like get the right like the bug state. So that's the intuition why QL might work better than the randomized thing. And we'll see like how it does work better in the subsequent slides.
So yeah, I have just a question. In this example, a wrong decision basically means that you're matching the string.
Yeah. That's that configuration. Yeah.
Correct. So of course it makes sense in this example what a wrong choice is. But if you have a different system that we're scheduling, it may not be clear. As in this case, we know that the wrong choice is matching the string and so on. But we can only know that if we do some kind of an analysis on, in this case, worker C, right? For example, if we had something where the bug was if you match every odd character in your string or something like that, then we would need a different kind of rewarding.
So actually, the three approaches basically they try to explore more. So giving negative reward, as in Akash's class paper, like gets the more exploration. That like here also we are not. Here also we are giving this negative reward to explore more. Not that we don't know the actual bug state per se in this algorithm where this. We just do a vanilla QL with -1 reward. It's just supposed to explore more.
Yeah, Bijan, I think that do you have the slide where you say what an agent and what an environment is?
Yeah.
I think you should put that first.
Yes, sure. Now, so maybe it'll be clear once that comes up.
Yeah,
sure.
Diganta, your question. I mean, you go to the previous slide. No. I think I'll address it. See here, your question was, I'll answer the question and maybe after that we can revisit so that, see, the reason I asked that is because, see, as an environment, okay, maybe you should go to the next slide, okay? This one. See, the amount of information, I think it's related to how much information the agent is allowed to observe, okay? Say in this case, if the agent is allowed to observe, of course, if the agent is allowed to know what that eta is, okay, then you know about the bad state. But you can expose only the length of the number of the length of number of characters that you've seen so far. Okay. Suppose that is all. That is, and that's why I asked Vijayan to put this thing so that people will know how much. Okay, so there is a control even in the RL environment. In general, you know, as little as possible. And he did say somewhere here, and I think, so in this case,
observing the state of the program is a counter M here.
Yeah, he's only doing counter M.
Yeah.
Then so, the agent does not have. Okay, that is, I think.
Okay. So okay. That
on this is the counter. We don't know that we don't even have the string like that.
Right.
Yeah, that's right. Right. So, it's not that counter. Kind of very without actually dwelling on it, and that's why. I also missed that.
Yeah.
But
okay.
In general, but then from the agent's point of view, this is no longer Markovian now, right? Because the string really determines whether or not we get a reward.
See whether, I don't want to get stuck. Okay, once again, since you're asking.
Maybe let's take this up once we have something, some more details.
So the Markovian and non-Markovian, if I say is based on whatever state information that the agent is able to observe. it is still Markovian as long as no, that's why I was careful in determining. I don't know what the definition of Markovian is.
It's not supposed to depend on previous states. That's what Markovian is. Like it just depends on the very previous state and not the other previous states. So.
Or rather, it shouldn't depend on the history of action, right?
Oh, but here I don't know. Yeah, Diganta, so I want to kind of interrupt here so that we can proceed. No. See, I don't want to get stuck on the definition of Markovian, but what I'm saying is, it is possible that it is not that clear. By exposing the length, you still don't know entire information about the state, okay? So your reward, etc., is based on only this information. That's how, in that RM, okay, if you move to the next slide, so it is entirely dependent that S, the Q table and the reward, everything is dependent on whatever is the agent observes, the state that he observes about the environment. Now, whether Markovian definition is, if it is just, okay, whatever state is exposed, as long as the reward function is a function of that state that is exposed and action, is that how Markovian is defined? Or we don't know. I mean, just because counter information is exposed, I don't know what eta is. Now, full information is not exposed. No? So,
I think.
Yeah.
So I think that so by Markovian you mean that given a state, you only make decision from that state, given that state information. But
correct.
But here's but non-Markovian is you're also seeing some history. So in a sense, this Q table itself is saving some history by this method, exactly in this method, because since this method only tries to figure out how many distinct states you may want to visit. So since here, if you keep the count, so that means that you have already visited the counts before that many times. So you want to visit the next counts, soon. So in that sense, it may be not Markovian.
Yeah, that is kind of what I meant. Yeah, but it may or may not matter at all in this case, because maybe we're not even depending upon the convergence guidance. Right? So maybe let's continue and we'll take this up in sometime later on, right?
Yeah.
Okay. Yeah.
Sure.
So
but this Markovian thing, the reason that I'm a little bit picking on that is because I've seen a lot of RL framework that they expose only part of the information. Now, whether that part here it is the number of messages that I'm counting. I mean, that I've received so far. Okay. But I'm only using that information at the current state, huh?
Yeah.
But in MDP you're not even allowed to use that in Markovian. You only have the state information. So by state, I don't think you can expose something that relates to that state. What I mean by that is, so suppose in the previous example where you were counting the length, so the length information itself is dependent on how we get to that length. So if we just randomly named it like some arbitrary name, then it would have been Markovian.
Yeah, but what if that I maintain count as part of the state in the environment itself? Expose the whole thing. Then is it Markovian or not? Because let's suppose in the markup decision state, I also put this counter information in addition to everything else, and I expose the entire thing. Then you're keeping state information as part of the state. Then, from the definition of how you reward function, you're making it based on the state only. But I can keep adding information to the state in a transition system or in an MDP to keep history information. After that, whether it is would you still consider it Markovian or not? See, I can always enhance my MDP with additional state information to keep track of history, right? And expose the whole thing. So, I think this is not germane to the algorithm here, okay, that they do. So Is it okay if I defer this?
Yeah, yeah. Yes.
Yeah, I think
Yeah, so I'll just briefly mention the problem statement concisely for once. So we are finding optimal set policies in a distributed system as a reinforcement learning problem and propose a new algorithm for biased exploration of the program state space towards semantically significant states for better coverage and bug detection. That's the description of what the paper does. So we are interested in finding those error states.
Let me pause.
Yeah.
Okay, I think it was not fair to Diganta. Diganta, I mean, this
sorry.
non-Markovian, why do you think is significant in, that it is, I mean, I didn't let you explain it fully. Why, I mean, here, I'm not exposing the entire state, okay? Why is it important from an RL, policy learning? You could learn more from that. Is that your point? Diganta?
I think you're muted. Yeah.
An easy here?
It's a bit unclear.
Huh?
It's a bit unclear. Okay, just a second. Is this better?
Now it is better. Yeah, it is better.
Yeah. So what I want to ask is, I mean, there are so the Q learning algorithm will only converge if it is Markovian. So that's the only reason I was asking. But then maybe later on they're setting it up in a way that is avoided, which is why I want to also postpone this discussion to later on, basically.
Okay. Yeah.
So
I think
maybe at the end we can think about whether it's Markovian and whether that matters for this algorithm.
Yeah, I think it does not matter here because he's using it in a that online kind of a mode where there's no separation of training and the listening phase. He just keeps running it. Okay. And as soon as either he hits a bug or he never hits a bug. Okay. If he hits a bug, he stops. That kind of a thing. Yeah.
Okay. So I think that might get cleared once we go through the algorithms. Like there's 3 algorithms once we discuss that.
We can revisit this. Yes.
Yeah. I think that's a good idea. Maybe
so this is the problem statement. And so now I should move on to describing this agent and environment RL setup. So the environment is a program whose configurations from the set sigma. User-defined abstraction function H sigma to S maps the program configuration to the abstract states representing the agent's observation of the environment. The reward function is, so like for the first algorithm we shall see, the reward function that I'm going to call neg-RL. The reward function R S cross A to R is a fixed constant value of -1 for all the state action pair, since that ensures that the Q values to decrease over time for seen state action pairs, thus increasing exploration, since RL tends to maximize Q values. The agent uses a Q-learning based scheduler that selects the action using a softmax policy over Q values. The agent maintains a partial Q value map Q S cross A to R, the state action pair to a real number, initialized to 0 for unseen state action pairs. The agent's action selection is based on the Q values, and it updates the Q value based on the abstracted path schedules. That's the setup that's the basic setup for both of the RLs, and the reward function shall change. And okay, so there are more in this.
Any questions there? Okay, that's so the basic reward function is -1. You will talk about more about what exactly it means. What is the impact of setting it to -1 later on? I mean,
So the intuition is key. Okay, I'll describe it in the algorithm itself.
Okay.
So main 3 RL-based approaches that are present in this presentation is the reward function is chosen to be -1 to increase exploration. That is the main RL. This is Akash Goel's paper. Now the bonus max RL that kind of keeps track of the number of visits to a state while exploration. This is the bonus max RL that occurred in Srinithi's paper. And finally, the waypoint RL, which biases exploration towards potentially buggy states. So this is kind of done semantically, and like, yeah, this is a bit involved, and this also occurs in a recent paper by Sunidhi. Yeah, for finding those buggy states. So yeah, let's specify this in a negative order. So this is a very this is a very normal Q learning approach that yeah, this is very Q learning approach where the reward function is taken to be -1. And so let's just go through line by line. So the actions are A1 to AN. Configuration is sigma. State is h of sigma. H is the hash function. Now for each A in A1 to AN, like we take an action for each. So do if QS comma is undefined, then QS comma is 0. So initialize the Q. I think X is a type. QS comma is a 0. So initialize the Q values for S comma A pair to 0. So the Q table is initialized to 0. Now we have this probability distribution over actions that is initialized to an empty list. So for each I belongs to 1 to n, we do this softmax thing. Di is q e to the power q s comma ai by summation j is equal to 1 to n e to the power q s comma aj. This is the probability distribution, the softmax probability distribution that we take. Now we choose I sample from D and return AI. So this gives the get next QL. So what action we shall take. Now the prepare next QL, it's input the schedule that sigma 0 to sigma 1 a dot sigma n minus 1 to sigma n, and L cap is initialized to HL. H is the hash of that L again. Set L cap to, that is set L cap to this thing. Now for each I from n to 1, do this maximum Q is equal to maximum of the Q values amongst all these actions, and update this Q value as Q s minus 1 comma si minus 1 comma ai. So 1 minus alpha Q is I minus 1 comma ai plus alpha reward is I minus 1 comma ai plus
this is basically
gamma max.
the Q learning.
Yeah, this is basically the Q learning. And once we put
even the R function, this is a generic Q learning.
If we put R equal to -1 here, then we get the Nick RL.
Yeah. Okay.
Thing. So yeah, this slide basically is the description that I just went through. So H is a user-defined function, a hash function. It's basically an abstraction of the program. Now, H sigma. Yeah, I think I'll just pause at this slide because this is just something that I mentioned. So the reward function that was not in the program was reward function is a fixed constant -1, that is R is comma equal to -1 for all is comma I. The idea is that the constant negative reward ensures Q value to decrease over time for the same state action pair. So for a schedule L, HL again denotes this abstracted schedule over sigma I replaced by it's sigma I. The QI schedule is parameterized by H and uses it to in get next and prepare next procedure. It maintains this partial map, which gets updated, representing the Q value. So get next gets the next action. Yeah, this was pretty clear. Yeah. Yeah, this probability distribution over actions is computed by the softmax policy here. Here.
So
action is sample from
intuition? What is your intuition about putting -1? What does it have?
So
I think maybe you should explaining that will help. I don't know if people got that point.
So the negative constant reward ensures that the Q value to decrease over time for the same state action pair.
Why is that?
If we keep on so like so if we keep on visiting the same state action pair, Yeah, so we should keep on getting -1 reward for that. If we like for that, the Q value for that state will be, if we have already visited it for some time, for maybe 10 times, then it will have the Q value of that state will decrease. And the RL policy is supposed to like go to a state to increase its Q value. So it will tend to avoid those states that it has already visited. That is the main intuition why it's just a constant negative reward should intuitively do the work.
So as a result of it, what
so
what
a
does-
result of
what
which
does the learning do?
it will imply if it's keeps on visiting the same state again and again, the Q value keeps on decreasing, but the RL wants to increase that Q value, so it will tend to explode more, like try to visit other states. Hello, am I audible?
Yeah. So I guess if the number of states is large, then it has the reachable state is large.
Yeah.
Then because of this, if you haven't visited some reachable state, it has the indirect effect of choosing an action that will lead to a non-visited state. Correct?
Yes. That is the intuition. Yeah, putting a negative reward for everything. That is the main idea.
Anybody
if
else
it keeps on visiting the same thing.
Yeah, questions about this algorithm here?
So of course, an obvious way to like think about it would be to maybe like we try to keep a mark on how many times we're visiting, and then update the Q value in such a way to also invoke that thing. See how many times we're visiting, putting a metric on that instead of just putting a -1. So that is being done in the next algorithm, bonus max RL. So that I shall describe. But for now, this is the scenario that we are just keeping -1 and hoping that, I mean, like it intuitively should visit more states. This should lead to more exploration. That's the impression.
Okay, any questions here about neg RL1 and the intuition that Vijayan gave? Okay. Do you have
I do have some questions, but I maybe
no, please, no. You feel free to ask. I mean, as moderator, I'll defer.
Sure. Okay. So I mean, maybe. So what I'm wondering is,
yeah.
So suppose we have some kind of, I mean, this is of course using RL, but suppose we have some kind of simple algorithm that will just keep track of whether I've visited a state and do just some BFS over the states, right? So how is this at all different from that? Because all that the sort of RL agent even knows about any state is whether or not we have visited it, right? It doesn't know any. So for example, in this ABC worker example, it doesn't know that this worker is matching a string. It doesn't know that there is, eventually a buggy state to be reached even, right? It doesn't know any of these things. All that it knows is that it has just, yeah.
So if I've understood correctly, I think that in the worst case.
Let Diganta complete his question. So yes,
oh, sorry.
Your observation is correct. But what was your question? How is it different from
what kind of system? Doing a BFS or DFS? I think.
Yeah, I mean, how is it different from doing BFS or DFS, right? I mean, we're not using any particular information to learn some policy that will, based on some information, smartly decide where to go.
Well, as opposed to like spin or something like that you're talking about?
Yeah. I mean, just basically. So I mean, this is even simpler in the sense that we're just if you just keep track of what.
Let Vijayan answer that, and then I have.
Yeah. So I think that could lead to, in the worst case, visiting all the states. But we are interested in trying to visit the interesting state. Like so here, so it's basically like finding a prime number or finding a prime number with high probability. So it's like the difference between randomized and deterministic. So here that thing would be deterministic. Here we are not going to deterministic, but we are trying to get something better than the randomized. That's the thing.
Sure, but I mean, see, even then the kind of distribution that we choose states based on, that is simply based on the Q values, right? And all that the Q values are telling me is whether I visited a state or not, right?
Okay. Yeah.
So ultimately, yeah, sure, that there is some kind of
I see the question now.
Yeah, there's some randomization, but the randomization is just it's almost like if you had randomized BFS and instead of just having some deterministic version of BFS, right?
I think
Yeah, I
that's
mean,
why
like you were randomizing breadth first search, but if you were coming back to a state, you were putting negative reward so that it does not keep on going like on and on the same states. So that's what you were doing basically here, like in this.
Sure. Yeah, but that is all that the
let me
randomization
interject
is.
here because so there are two points. I think part of it Vijayan did. See, the idea here is, that's why I asked Vijayan if you were going to put any experimental comparison. So here for his idea of this neg R1 was not to compare it with spin, okay, but rather compare it with just random exploration, okay? You pick random schedule. Even without information about just this one, by making it learn different things, it tends to catch bugs, okay? That is their
better than random schedulers.
Better than random
Yeah.
Okay.
And while treating the program as a black box, right?
Well, I mean, exposing some state information, okay?
That is this hash function is doing that, like what state we are getting from the program.
More than the hash function, as you define the hash function, yes. So as a matter of fact, I think it would be helpful to answer Digant and the rest, maybe the audience is having the same question, to put the table for that example that you showed of random versus this one, okay? And the other part of the answer to your question is it scales much better than symbolic methods, okay? Or
that I agree. I mean, I'm also not asking to compare to symbolic methods like spin, because they take much more information from the program into account and so on.
I think that line of work is certainly useful, but to me,
but that's not that is not the comparison that I was trying to get at. I'm sorry to interrupt, but but anyway, so I think what I'm trying to say is that I can understand this will be better than random, right? But if in this table, for example, if we had another column where what we were doing is not some RL based technique, but also not some random scheduling, but simply this is that we just keep track of the hashes of the state seen so far, right? Just have a set which keeps track of the hash of the state seen so far. And while we're scheduling, if the next state that we're choosing is if the hash of that state is inside our state, is inside our set of hashes, then we simply don't visit that state anymore. I mean, we don't explore from that point forward anymore, right? So just some simple thing like that, I wonder how it would compare with this one, right? Because it seems like we are not really using the state information in any way other than just to keep track of whether we visited it or not, or how many times we visited it, and so on.
So if I can
Arpan.
So in a DFS, what do? You go to the end state. You from the stack you remove the last state. You visit the state before, and you see what are the transitions is possible from the previous state of the last state, right?
Yes. Sure. Yeah, go on.
Yeah. So, but here what is happening? You explore the whole state. Then you are again starting from the initial state, and from there itself you will take a different path. So intuitively, I mean, it may be. It's not ideal to. I mean, it's not right away clear. Why is this will be better than the DFS? But the DFS will keep on searching through the single path again and again. It will remove the one element from the stack, again explore all the branches from there. Whereas this thing, it will try to go to the before even visiting the same branch again. It will go to other branches again, and it will try to find some new paths there. Once it finishes exploring all the other branches in the first step, then it goes to the next. Next path length.
Yeah,
then again,
yes, I think that's an important point, because it learns. See, it is not you explore for execution runs, and then if you have not visited, then you learn from something that you from your previous execution run. So I don't know. I think that is what you're saying is if it is whether this is, they're only comparing with random, but I do give it to you. It is different than what spin is doing because it is learning. Maybe it is a little bit close. I mean, better thing would be for fuzzing, okay? Comparing it with that, because each time it is learning from something, from finite execution runs, and then trying to do something different from all the previous execution runs. Okay, so in that sense, it's different than what spin is doing, where you're exploring all the successors from the thing, like what Arpan pointed out. But whether, if your point that you're making is with the non-RL learning frameworks that do just as well as this, I think they do. Okay, fuzzing, for example, is something that outperforms this simple -1 kind of a function. Okay.
Okay, sure. Yeah, I mean, I have more discussions maybe on this point, but like maybe different. Yeah.
Yeah, I think let him go through 1, 2, and 3. Okay. So then I
Yeah,
think,
yeah. Maybe we can have this at the end, and yeah.
yeah, and I think some of these things are a little bit more sophisticated. The other versions that may get partly your question answered. Yeah. Okay, which does very well. So, but I understand where you're getting at. Okay, why this simple thing? You could devise lots of other methods. Okay, that can potentially be better than this. Yeah.
Yeah, I mean, I'll expand on that point a bit, but maybe let's talk about that later on.
So this is about neg-RL. So yeah, moving on to bonus max RL then.
Yeah, you had some neg-RL 3. What does that mean?
That's
just the number of slides.
Sorry about that. Yeah. I don't know
anybody else have any questions on the simple, basic method of -1? Yeah, RL -1. Yeah, I mean the simple thing. Yeah? Okay, then please proceed.
Yeah. So now we basically chose the reward equal to -1 to increase exploration. Now in bonus max RL, we should keep track of the number of visits in a way. So let's look at that. So yeah, in bonus max RL, so the algo goes like, so we have input this alpha, gamma, epsilon. These are some parameters.
But no, you didn't answer my question. You showed the table. Okay, fine. Yeah. Was there any question about the table? I mean, I know that we just put the table again to see if people got. Yeah. So this was for which benchmark?
So this is radius benchmark over random, bonus max RL, and neg-RL. This is ETCD.
But this you have not.
I don't exactly know the details of the benchmarks, so.
Yeah. Okay. So these are all what are the numbers that you're comparing the percentage of buggy.
Yeah, the exploration in some manner. So the more better. So here, this neg-RL is doing better than the bonus max RL and randomized RL for ETCD, and for R, so somehow bonus max RL bet this by a large margin. So yeah.
Yeah, but neg-RL is not uniformly doing better than random, is it? Yeah.
No, it is uniformly doing better than random. It is having some competition with bonus max.
Yeah. Okay.
Yeah. So yeah. So now we are doing the initializations. We are having the Q value set to 1 and the values set to 0 for all S, state action pair. So we are having this new episode as resetting this trace to empty array. Now we define this that is supposed to find the action. So X is sampled uniformly at random between 0 and 1, from 0 and 1, 0 to 1. So if X is less than epsilon, then return action U action uniformly random action. Otherwise, take argmax of Q S, the action that maximizes the Q value. record step function does is to it updates the trace to state action and the new state. So it takes the state action and new state and it just updates the trace. Now process episode for each episode for the length of trace to 1, for I is equal to length of trace to 1. S comma S prime, S comma A comma S prime is takes the value of trace I. So it takes the ith value of this trace. E is the Vs comma A plus 1. Vs comma is the value at S comma A. E stores the value plus 1. Vs comma A is set to T. And R is set to 1 by T. This somehow makes sure, basically counts the number of visits. This is the reward. So if I is less than length trace, then QSA is updated as 1 minus alpha QSA plus alpha maximum of R comma gamma max A prime QS prime comma I prime. The regular Q value update, and QS comma A is otherwise if it's greater than trace length trace. 1 minus alpha QSA plus alpha
Can you
max
give
R
a
comma
high-level
Z.
intuition as to what's going on? I know that you went through step at a time, but what is going on?
What is?
Can you give a high-level intuition?
Oh, what is going on? Okay.
Yeah.
So this is the regular Q value update. We are taking this reward function. The reward function as 1 by T, which is the 1 by value at a value function at S comma A. Plus 1. That is what we are doing as the
And the value function is keeping how many times you visited, correct?
Yeah, in a way. So the value function.
That is exactly what it is doing. Yeah. So for each action pair, so then it is.
Yeah, T is basically the number of times. Value function. You are updating this, and you are storing that. Yeah.
And you give. So here you're not giving a negative reward, but rather you're giving always positive reward, but which are kind of gradually decreasing based on the number of times you visit. Yeah, that is what you're on.
Yeah.
Okay.
Yeah. So
what is the? Yeah. Oh, that's what you're still in it. Okay, fine.
Okay. Yeah.
I thought you were going to an algorithm.
This is the summary of the algorithm. I'll just read.
Any questions people have on the previous one? So it's just if I, correct me if I'm wrong, Vijayan. So basically, what you're doing is how is it different from neg RL in 2 ways? That the way reward function is different, and it's not.
Yeah.
Earlier you had -1, so now you're having just a positive reward, but that is geometrically in some geometric progression decreasing, okay, tending towards 0 as you visit more and more times. Okay.
Yeah.
But I also for example, in 20, it is quite different than the way standard Q learning is happening. Okay, which you did not describe. Okay, so usually you find you take this part here is quite different. There's no difference.
It's just the trace. If we are exceeding the trace, we are not having these other functions. That's all it is difference with. This is leading to this conditional statement. Otherwise, it's the basic Q learning only. You pick randomly and
the basic Q learning thing. You're right. Okay.
Yeah.
Because they have factored out differently here. There's still the minus thing is there. Okay.
Yeah. It's from a different way, but the notations are a bit different. But yeah. Yeah, alpha is a parameter. Like alpha, gamma is basically the discount factor. Epsilon is the threshold sort of thing. These are hyperparameter to another. So I'll just walk through the summary again. So the algorithm implements this bonus max RL exploration policy with hyperparameters alpha, gamma, and epsilon as input. The action selection mechanism, it uses the standard epsilon greedy strategy. With probability epsilon, a random action is chosen with probability 1 minus epsilon. The action with the highest Q value is selected. The process episode function updates the policy based on purely on exploration bonuses, as no external rewards are provided. The policy maintains a visit count table, ds, a, for each state action pair. This is the value. Yeah, it's the visit count. The internal exploration reward is computed as 1 by t, where t is equal to v s, a is the number of visits to s, a. This reward is high for new states and decreases as the pair is revisited more often. So yeah, this is something to stress on right here. So for every transition s, a, s prime, the visit counts vs, a is incremental. The Q value update rule is Q s, a equal to 1 minus alpha Q s, a plus alpha maximum R, gamma max epsilon Q s prime, a prime. This update differs from the traditional Q learning by using max instead of sum, focusing only on the best reachable future state. The update rule favors the transition that leads to a new state and devalues other visited states, pushing Q values towards 0 over time in a stale region. This method does not guarantee an optimal policy learning in environments with explicit reward functions. So in particular, bonus max RL may favor shorter paths that reaches novelty faster, even if longer paths have higher cumulative reward. This is all because, like, instead of choosing the traditional summation, we are using the max. So this shorter paths might be more favored. Like, it's more like, yeah, like. So despite the potential suboptimality, bonus max is effective in distributed system testing as it aligns with the goal of aggressive state exploration. So here we don't really are so much interested about how we reach the state. We just want to go to that state. So that is why this max instead of sum is justified. And even if we are not finding those like longer paths with higher cumulative reward, that doesn't matter to us, because if we reach the error state, we'll know. So, and that's what we want to get there faster. So this is the bonus max RL. So is this clear? Like how this is in contrast to the previous neg RL and why it should work? Is that clear?
Any questions? Diganta? Anybody? Arpan?
No, not at this point.
Okay.
No, that's fine.
So, yeah. Okay, so I'm moving to waypoint RL, which is a bit more involved. So like unlike so unlike this previous two where we were tweaking the reward in like the tweaking of reward from neg RL to bonus max RL was kind of intuitive. Like here we are keeping one more count of number of visits. But waypoint RL, which is a biased exploration towards potentially buggy states, this is kind of more involved, the generalization, and we should discuss that now. So yeah. So first, let's get started with the basic functions. And so here we have something called predicates as inputs. So predicates are generally played 1 to played n. One time is I'm going to call this top and bottom. Alpha, gamma, epsilon are the Hatta parameters. So initialization, all the Q values are initialized to 1. Vi, S, I is initialized to 0 for all the state action pair. The new episode is trace is resetted to 0, and the reach is resetted to bottom. Yeah. So if I is equal to n to 1, predicate I initial state is equal to 2, is equal to top, then active predicate is I, right? So yeah, this is something to focus on. Then define pick. Pick is another, like it takes input a state and an action, and X is chosen randomly from 0, 1. If X is less than epsilon, then alpha is A is chosen randomly, action is chosen randomly. Otherwise, epsilon greedy. Otherwise, I is chosen as active predicate, and we take this argmax A qi s command. So like the maximum action that maximizes this qi, the active predicate wala Q learning, things.
Yeah. May I interject here, Vijayan? So
Yeah.
before you get into the details,
Yeah.
maybe it might be help. What exactly is this algorithm trying to do? What are the predicates supposed to mean? And what is it? What are you trying to make the agent learn towards? Okay, what can you give the high level intuition on that?
Yeah.
I'm just
so the main idea of this waypoint array is to so waypoint array allows to specify target stress in the form of predicates that should satisfy. So it's supposed to search guided by semantic knowledge from the states. So that is what our so it takes input a state of predicates that kind
specifically
of
what is it trying to bias towards? It's trying to bias towards those execution sequences where first at some point predicate 1 is satisfied, then predicate 2, predicate 3, and so on in that order. Is that right?
Yeah.
Okay.
1 second. Yeah.
Okay.
Yeah,
So
predicate. Yeah,
these predicates are over states, and you're supposed to make this algorithm.
So here we are having different Q tables. Like ith predicate has its own Q table.
No, I understand. That's an implementation detail, but yeah. So here you're trying to make the thing bias towards specific scenario, where a scenario is defined as those execution traces where these predicates hold good in that order.
Yeah.
Okay.
So
now you can go through the detail, please. Continue.
Yeah.
Just wanted to help.
So this epsilon greedy, it's a bit not traditional epsilon greedy again. Like here we take I as the active predicate, and then do the epsilon greedy approach on this ith predicate. We just look at the Q ith s comma Q table and take the maximum action maximizing that Q value. So there is record steps method that if a state is reached, so the reached is supposed to store whether we are reaching it at last, whether we have reached the buggy state. So if reached is bottom, if reached is false, for length predicates to 1, if predicates si is true, then next active predicate is I, break. If the next active predicate is n and 1 time is equal to true, then reached is true. We have reached. If next active predicate else next active predicate is n. So here we are somehow selecting this predicate and the active predicate we are selecting until we are reaching the buggy state finally. Now trace is being updated as trace equal to trace plus s comma a comma s prime comma active predicate comma next predicate. Now active predicate is updated to next predicate. This is record step. Now this is the process episode for this waypoint array. So for I is equal to 1 to length trace s comma a comma s prime comma p prime. P is the predicate, P prime is the next predicate. Trace I, which we get from trace I. So if P is equal to n, then reached final is true. Reached step equal to I, break. So if we have reached the nth predicate, so for the nth predicates, we just first find out if we have reached the final state. 1 second. So the final, it just checks if the nth state is reached, then this final is true and the reached step is I, and then we get out of the loop. Now for again length s to 1 is equal to length s to 1. Do s comma a comma s prime p comma p prime is equal to trace I. pick the upper value. And then t times visited is equal to vp s comma a plus 1. Vp s comma a is updated to t. Explored is updated. It's like the bonus visit thing. Explored reward equal to 1 by t. So if p is equal to p prime or p if p is equal to p prime or p is equal to n, then if length of trace is less than is greater than I, then we update the q value like this: qp s comma I is equal to this 1 minus alpha qp s comma I plus alpha max explore r explore reward minus comma gamma into max f prime qp s prime comma I prime. And if that is not the case, then qp s comma I is equal to 1 minus alpha qp s comma I plus alpha max of q explore r comma 0. Now, if p prime is greater than p, so if the next predicate is more than the current predicate, then log r is initialized to the predicate bonus is given to be 2. Otherwise, prog r the progress bonus is initialized to 0. And if reached final, then d is equal to reach step minus I minus 1, and final reward is given as gamma to the power t into 2, and the qp value, the px q table is updated as 1 minus alpha qps comma I plus alpha this max explore r comma gamma into log r plus final r. So this is the reward for the pth predicate. So it's the reward function is like bonus max value, but we are biasing it with our specific predicate inputs, and like maintaining different. So the summary is maintaining different q tables for those n predicates, and doing the exploration in an interleaved fashion between the predicates. That's the main idea.
Yeah. So if I
Yeah.
made some, I mean, you have some informal, just like you had for before, some informal descriptions. There's a lot of details here that I'm not sure if everybody followed. So basically what you're trying to do is, as the Q learning simulates the environment more, you try to propagate the truth value of these predicates, okay? And see if, from one execution to the next, if there are traces where one or more of the later predicates became true before the earlier predicates, then you kind of force them through these Q table propagation by maintaining different things to make it update the Q tables in such a way that it learns to...
those predicate values, the satisfiability of those predicate values also come into play while running the Q table. That's the idea.
Yeah, that's what. So the Q tables are kind of updated conditionally. Yeah.
Yeah. So I think after going through the summary, it might be a bit more clear. Like I just go through this summary once. Like whatever I went through the details.
Yeah,
but
please, if you don't have the summary, please go through that. Maybe that will help because
that is
very hard to understand.
Discussion will be more easier after going through the summary. So this waypoint array uses a sequence of predicates, pred 1 to pred n, to guide exploration. Pred n defines the target space, while pred 1 is always true. A separate exploration Q table is maintained for each of the predicates. At each time step, the highest indexed true predicate becomes the active predicate. So we are not going. We want to be okay. So sorry. We are going like the highest index predicate is all that we're looking. The agent selects action using the Q table of the pth predicate and stores the transition S, A, S prime, comma P prime in an episode trace, where P prime is the active predicate in S prime. The process and P is the active predicate status. The process episode method updates this Q value using the trace. It checks if the final predicate pred n was reached and stores the index. Performs a backward update for each step. S comma S prime, comma P prime in that trace. Now, if P is equal to P prime, it uses the bonus max RL update rule. QPS comma 1 minus alpha QPS comma plus alpha max explore reward comma gamma into max prime 2PS prime comma prime, where explore reward is 1 by T, where T is being the visit count of S comma as the bonus max RL. If P is not P prime and P prime is greater than P, progress bonus prog R is equal to 2 is added. If the final predicate was reached later in the trace, an addition reward is given as final R is equal to gamma to the power T into 2, where T is the reach state. Reach step minus I minus 1. The final, so this is basically the discount factor taken into account like this. Sure, like if we just do too many things, then after discounting this, basically is the final reward. The final update is, in this case, becomes QPS comma A to 1 minus alpha QPS comma A plus alpha maximum of explore R comma gamma prog R plus minimum. So this more or less, after that, we have these hyperparameters which are alpha, learning rate, gamma, the discount factor, epsilon, the epsilon greedy selection. A Boolean flag one time indicates if one spread n is reached, all further states are considered to be target space. If one time is true, reaching thread n sets reached to true, and all the subsequent transitions use the Q table for thread n. Okay, so the init methods and the init method initializes all Q table per predicate. The new episode method resets the trace and the reach flags and determines the initial active predicates. The pick method performs epsilon greedy action selection using the Q table for the current active predicate. The record step method updates the active predicate for the next state and records the transition, setting the least flag if the target predicate is encountered. So this is the main thing that is happening. We are kind of doing using the reward from bonus max and like checking if those predicates, the input predicates, are being satisfied one by one. Is the overall like high level view of the algorithm clear to some extent? The waypoint RL. Okay. Hello, am I audible?
Yeah.
Yeah. Okay.
Questions? I have one question. How are the predicates determined?
So it's the predicates are of course problem dependent.
Yeah. Okay.
So maybe you are having some intuition of where the errors might lie, and you are using them to. So, like for example, in that worker APC case, what could be a good predicate sequence? So the thread 1 is always true. The thread 1 will be like the, I think, actual target thing. No, what could be the predicate?
Yeah, like for example, I mean, if it gets set to -1, there will never be an error, kind of a thing, no? So that could be one predicate. Any buggy thing will have to completely match, no? Or it's the other way around. Something like that.
Oh.
No, okay. Does people have any questions about this thing? Okay, so
I didn't understand the answer to how the predicates are determined. The question that you asked.
Can you try?
Yeah, I'm thinking 1 minute later. Yeah, it's a determined. So
it's fine if there's like an intuition. That's all.
No. I think they didn't think. I mean, I can comment. I mean, do you have anything to add, Jim, for Shobit's question?
No, not at the top of my mind. I can't figure out now what could be an interesting, like, good
if
predicate
people
for that.
have notions of, for example, I mean, I think Pigeon did answer one part of it. Let's suppose that, I'm kind of stating one part that he said, which was in general terms. Let's suppose that, there is protocols, and, since you are working on protocols, Shobit, I'm giving this answer. So if, leader election protocol, that if there is at any point, if there is, some nodes try to send duplicate messages or repeated messages to distinct nodes, votes, okay? That is a buggy scenario, okay, followed by maybe there is a state in which the count is wrong or something. So these predicates are designer's intuition, okay, as to where the bugs might lie. Yeah, Ken, there's some background noise. Someone who
Sorry, one second.
that, yeah, if you could, yeah. So, yeah, that is one. Or, this could be, if certain invariants are to be preserved for correctness, the negation and the invariant could be in this thing that this, you have to first reach this state, that's, next that, and so on. The negation of such invariants can be a source of predicates, okay? Together, they define certain scenarios where bugs are likely to occur.
So I have also included this intuition from cuboid problem. Maybe that might throw some light on
Why
this.
don't you explain it? Why don't you answer it? Yeah.
So this is almost the second last part of the thing. So experiments intuition with exploring cuboid example.
So this is an actual example where
so let me just go through the figures one. Like it's a heat diagram. It's like the brown parts of explode parts and like non-brown parts are not exploded. Like how many times it has been exploded, something like that. So like overall, like the result looks like for random exploration, this goes to. So these are like the 5 cubes that are supposed to be how much they explode. So the random exploration does the exploration till cube 1. Bonus max does it a bit more, cube 0, 1, cube 0, 1, 2. So
what are these
bonus
cubes?
max,
these cubes are predicates?
Yeah.
So like where after exploring certain things, you have to go to cube 1, cube 2, cube 3, is it? Yeah. What are these cubes?
So that the cuboid problem is the environment is a 3D cuboid with the state space defined as GWBD, where D is the cube index, W is the WBD are the spatial coordinates with each cube. Radiant states starts at 0, 0, 0, 0, 0, 0, 0, and can take actions up, down, left, right, above, below, into, and disarray. These are the possible actions the agent can take. Into action moves the agent to the next cube via doors at the specific position. So for example, 055D into 1000. So there's an action into where they're like different cubes numbered 0 to something, and so if you are at the 0 cube and if you're at 5, 5 at certain depth E, if you do an into function, then you can go to 1000.
There's a particular condition that has to be satisfied in order to it's like a door from one cube to another cube.
Yeah, it's a door. It's a door.
It's a door. Okay.
There's a so reset that turns the
so these
So this is the setup.
So those doors have to be satisfied in order to move forward.
Okay? They're trying to So like maybe so in the depth abstraction, with different so for example, here we might possibly give the predicates as like where might the door maybe in the northeast or something, or maybe in the something like that. We can have such predicates as for the bonus max order exploration. Oh, is it a bit more clear what could the predicates be for bonus max? Sorry, for waypoint order.
Shobit, you asked the question.
I think this is.
This is like a game example where if you want to
Yeah, this is
to see if it did this, then it may not be a good thing. Yeah. Going through that.
Yeah. So, okay. Yeah. Okay. So the reset depth turns the agent to the depth 0, modeling state resets. So with 6 cube of size 10 cross 10 cross 6, the agent runs for fixed number of steps per episode across multiple episodes. Bonus max RL achieves greater coverage than the randomized exploration, but struggles to reach distant cubes within the episode budget. Adding a bonus reward for reaching cube 3 is ineffective if the agent never gets there, illustrating the limits of our naive reward strategy. So here they added some extra reward here in the cube 3. The bonus max RL did not even explore much of the cube 3, so did not get much far from it, was stopped here itself. But the waypoint RL somehow figured the reward did not explore all of the parts of this cube, but this part, once it got there, it somehow, so I think, yeah, so so the intensity, yeah, achieves better exploration than random, the bonus max, covering more cells. Second, unbiased exploration struggles to reach cubes away from the starting point. Third, choosing an appropriate state space abstraction can lead to better coverage, but it can result in reduced capabilities of systematically exploring a target subspace. While waypoint RL is able to effectively bias the exploration towards the target cube and almost fully cover it. So adding this cube 3 is ineffective if the agent never gets there, illustrating the limits of the naive reward strategies. Introducing an abstraction by removing the depth reduces state space and improves the cube coverage, but sacrifices depth granularity. So here we are having doing the exploration at a particular depth. Waypoint RL splits the tasks into reaching the target cube and exploring it thoroughly. Waypoint RL uses this Q table and reward functions for each task, allow targeted and fine-grained exploration. Intermediate waypoints, example reaching cube 1, reaching cube 2, guide the agent to cube 3 efficiently. Waypoint RL generalizes the reward approach via target predicates associated with the Q table, achieving both efficient navigation and full depth exploration. This setup is like a distributed system where the state transition depend on the message interleavings and events like group decisions or timeouts. So here are the predicates, an example is reaching cube 1, reaching cube 2, reaching also trying to explore that cube. So those are the predicates that we can give to waypoint RL, unlike bonus max or neg RL. So that's the effectivity of waypoint RL at a K level. And somehow this setup is like a distributed system where the state transition depends on the message interleaving and events like group decisions or timeout. So I don't exactly know the details of the distributed system, but I understand. I have the intuition to why waypoint RL would lead to greater exploration in this cube world problem, and that somehow will be essential for certain distributed systems as.
So what here?
These are
point RL is not in the table at all. Why?
Okay, the next table has a more depth coverage of.
It's only
because I think this is the no predicate scenario. So we are just comparing random bonus max RL and neg RL.
So they just
here we are having this predicates.
In the previous table, they are just exploring how many distinct states it covers.
It's just predicate-less things. So because we are not getting any advantage of predicates in this.
Oh, that I understood. My question was, what is it comparing?
Oh, so coverage. Okay. So this, okay. So this is a benchmark Redis strip. This is not the cube world benchmark. This is, and they have certain metric on coverage, which I don't know exactly about. But I know if it is more, then it's more coverage. That's all I know.
I believe it's the number of distinct states, I think.
I see. Okay. But like, okay, perhaps this 0.9, I don't understand then, but maybe they ran it for many times and this is the average. Maybe that is the thing.
Could be, yeah.
Yeah, the expected value plus minus the thing.
Yeah, for
the expected value plus the variance. I think the standard deviation.
Real protocols here. What I can read. Okay, they are consensus protocols. That they are.
Yeah, these are protocols. But yeah, these are protocols. I don't know the protocols, but yeah, these are the names of certain protocols.
Okay, so how many more slides do you have? I think.
I just this is the last section of remarks and similar work, which I can just like rush through.
Okay.
I'll just like wait like for 1 minute to like have a look at this table.
Yeah.
And then I can move on to the next slide. So here, these are the benchmarks with like number of predicates they're giving. And this is where the waypoint array is outperforming the other methods by decent majority. Like it's 24K, it's like 5K, 2.3K, it's 20K. Okay, here waypoint array did not help much. But here it's like 30K, it's like 5K, 3K. This bonus array in that order, like waypoint array. So almost in the decreasing order. This is performing a bit. Okay, sometimes neg is actually performing better than the bonus max array.
So I presume the numbers here are each tool is run for a certain number of runs, like say some 1,000 or 10,000 or
yeah.
And how many of them were able
to
bias explore that particular where all the predicates are true? That's what is being measured, I guess, no?
Yeah. So yeah, I think so. Yeah. So the number given this number of predicates, like bit. So predicates, I think they are supposed to guide the exploration. It's not that they have to be set. I think they're being used to guide the exploration, and you are using that in the details of the code.
I see.
Where they are being satisfied or not satisfied.
So that they are only measuring whether the bugs are found or not.
Yeah. I mean, it's probably that in the cube 3 there are errors, but it's not like necessarily we'll have to get to cube 3. Even if we not go to cube 3, we can also get a lot of errors from Q1, Q2. That doesn't matter. We want to get a lot of errors. That's all we want to find. But the predicate that cube 3 has a lot of errors, that will guide us there. So
okay.
So that's the idea, I think. So yeah, so this is the unique. Okay, yeah, average number of uniquely explored state plus minus standard deviation. That is exactly what these numbers are.
Okay.
Okay, 1 minute.
I think you should.
Wrap up. Sorry. Yeah. So remarks and similar work. So systematic exploration techniques are scalability issues due to the large state space in the distributed setting in the distributed systems. The deterministic way of exploration. Model-based testing also struggles to enumerate all possible failure scenarios. Randomized techniques are effective, but inducing arbitrary failures like node crashes and network partitions. Other randomized methods include this probabilistic guarantee for bug detection, partial order reduction to reduce state function, state space, standard fuzzing via input immutation. Verification approaches aim to eliminate the testing by proving the correctness or generating codes from the verified specs. But rarely used in production, bugs can still occur at the interface between verified and unverified components. RL-based approaches for testing. Q-learning can be applied to concurrent and distributed systems. Custom reward mechanisms encourage exploration, but may not bias exploration effectively. RL has also been used in input generation, parameter tuning, and control systems failure in induction. Reward-free exploration. So theoretical guarantees over state coverage using decaying reward augmentation requires polynomial of 50 degree number of episodes in state action space size. Ineffective and practical for large-scale systems and hard to bias exploration. The paper's approach extends pure exploration with semantic reward augmentation using programmers' knowledge, enabling effective biasing. Hierarchical RDL splits tasks into subtasks with learned policies and global coordination. The paper's method instead uses a fixed priority waypoints without policy reviews. The reward missions reward machines offer structured reward specification and decomposition, enable hierarchical learning and efficient policy optimization. Not applicable since the reward depend on actual system transitions, which
I
are
think
not
this
coupled
is a
from
good way to lead. Okay, so this is some similar works. I think reward machines is the topic of Varadha's.
Yeah, that is. The paper mentioned it, and I sought to like add it in the last section to like all the possible words and like some passwords and the possible future directions. Temporal logic goals in order use automated to define the goals and subgoals as intermediate automaton states. Simulation of the transitions based on temporal subgoals is infeasible with real world due to limited instrumentation. So these are possible these are the things that probably they have tried and they have like not gotten far because of like these are purely the limitations that one might actually like try to get a workaround.
I don't think these people worked on anything. This is just they have listed it for related works. That's all.
I see.
That's all. That's all.
Yeah. Reference. Thank you. Yeah.
Okay. Any questions?
Yeah. Questions.
Diganta, you want to follow up with any of your earlier?
Yeah. So I think earlier follow up was actually clear. I mean, Arpan had posted a message which made this sort of clear, but regardless, I think I had a separate question, which was this. See, I think this will perhaps depend a lot on how one ends up choosing the state that the policy is able to observe, right? So, for example, in this ABC example, if one has, let's say, some other counter n, which is just incremented every time you see a message from either A or B, and if one makes that a part of the state that the policy is able to observe, then the policy will never learn to explore more interesting states because every state to it is equally novel and more interesting, right?
Right. That's right. So you can see, you can fool it. Yes. I think
so how do they?
I think the just following, I think this, yeah, you're right. If the distinct states, you just add some junk portion in there.
Right.
And you can easily fool it. And Arpan has lots of examples for that. And that's why your original idea of, okay, adding something about biasing towards bad states, okay, that information would be helpful, okay? And this predicates is, no, there are two parts to your question. One is, it is sensitive to how much information, what part of the state that you provide, make it observe. So in that sense, I promise that you remember that Bijian early on, he said this is a stateless method, okay? It's kind of not stateless at all, okay? It is state, because you have to have state. I mean, otherwise, how do you even give reward function? And some aspect of state agent has to observe, okay? So it's kind of in between completely stateless and stateful, okay? Unless completely stateful or symbolic methods like model checking and so on. So, so it is.
We are somehow doing some sort of abstraction with it, using that hash to like just focus on some states and not the whole of it. That's
yes.
Yeah. So how do they discuss? How do you decide which states to focus on? Is that left to the user? And if so, how is the user expected to kind of do that? Or is that?
I am not exactly sure, but I can like post the paper and like.
Yeah, I think just like this is my own comment. I don't know if they have, when you construct a model, abstract model for verification, how would you do it? Okay, you have certain properties, etc., and then you do it. Okay, I mean, and you figure out what is important, what is not important. No, that can be a guide here as well, but that still maybe too much information. Okay, so I think if I'm not mistaken, Vijayan, I think they do discuss a little bit of that. For example, if it's a consensus protocol, information about when you achieve quorum or not, information about whether something is crashed or not. Those kinds of things are important. Otherwise, you can't even express what your buggy state is. Huh? So at least that much information you have to expose. I think they use those kinds of information to do it. But your earlier remark of rather than just making simple reward functions, it has to be something a little bit more, more complex one that exposes some information about what sequence of events lead to a buggy state, okay, which can be part of your specification.
So there are in the paper it mentions that different hash functions they can take actually. So, but I think that is also in like Akash's paper himself. So the hash functions that are RL, different some examples of hash functions they can take, which I think to make the slide cleaner, I did not include those, but that paper was mentioned in the recent work.
Okay.
Yeah, but
so I can actually pull up that paper and
choice of hash function is for getting compactness of Q table, and how much of it is for determining what semantic information that you need to expose. It's unclear. Okay.
I see.
Yeah, but those are two separate constraints that are going to be guided by the hash functions at the same time, right?
Yeah, I think we are, any other questions, because approaching 4:45, so it's,
Yeah. Maybe this we can
12 minutes late, so I think
this
we
discussion.
have to end here.
Yeah.
Can we move on? Any other questions?
Yeah, sure.
Yeah.
So
we
yeah,
need to move on. Okay. Stop sharing, and I will let Vardhan take over.
Okay, thanks. 1 minute of just structure. Yeah.
Hello. Hello, am I audible?
Yeah, it could be better. Somehow you're feeble.
Now?
It's better now. Yes.
Okay.
You can share now.
Yeah, please could you give the co-host access to Vardhan tab, the another account?
Oh, I see. Okay.
Yes.
I see only one Vardhan here. There here.
Yeah.
Yeah.
Yes. So let me start sharing the screen. Is my screen visible?
Yes. Is it visible to everybody?
Yeah.
Yeah.
Okay. Yes. Thank you. So yes. Today I will be presenting the paper titled "Using Reward Machines for High-Level Task Specification and Decomposition in Reinforcement Learning." So one of the first goal in this paper is to define what is a reward machine, and after that use it to do Q learning on reward machines itself. So before I even begin with the problem statement, I will talk about some problem with the current before writing this paper, the problems which were there that they had to come up with something known as reward machine. So one of the issues that was regarding reinforcement learning, that reward functions were taken as a black box. So the agent did not have any information about it. So it was like a black box rewards. Apart from that, quantifying complex tasks was much harder through a single reward function. That's why also they came up with dividing the major task into subtask and then talk about it. And also because it was much more complicated and decomposition became much harder because everything was much intertwined. So this caused slower learning. So this was one of the major reasons why reward machine was defined as in the paper. Apart from that, there is one reinforcement learning technique known as hierarchical reinforcement learning technique, which I'm also not very much aware about. I only know some very basic which I checked on internet. So when you're using hierarchical reinforcement learning, there is no guarantee of convergence to the most optimal policy. So it can converge, but to a local optima. That too in the discrete domain itself. So these two are the major problems. That's why this paper talks about how to resolve these two problems. So in order to resolve the first problem, they come up with a structure known as reward machine, which I will talk about later. So for now, I'm just specifying what is a reward machine. So in order to understand that,
Can
here's
you
one example.
full screen?
Full screen. Is it
Yeah,
not
no,
visible?
no. Yeah, in slide mode or something, because you are, it is full screen, but
Yes.
somehow you are, yeah, it is okay now as long as you show the full slide of every slide. Yeah.
Yes,
Okay.
yes. I will ensure that the full slide is visible every
Okay,
time.
good. Thank you very much.
Yes. So yeah, to understand like the need for this reward structure or reward machine, we will talk about later. Let us take this example. So here is the office grid word. So we are starting at this triangle. And there are multiple spots which have been named using some alphabets A, B, C, D. And there's some coffee machines placed at these points. And there's an office and there is a mailing place where you can mail. So we can have multiple tasks in this office grid word starting from this triangle colored purple. So one of the tasks would be start from this area. Okay, sorry to I forgot to mention there are some stars as well, which are decoration which you need to avoid. Otherwise, it might break, right? So one of the tasks could be to get the coffee, avoiding the decoration, and deliver it to the office. So if you see this blue line, this blue arrow, it avoids the decoration, it gets the coffee, and reaches the office. So this is a possible way to reach it. I also need to mention that wherever you are, you have four actions that you can take. One is either you can go left, right, upward, or behind, like downwards, right? So these are the possible action, and each block are states. So that's how you will move. And another example of a task could be that you get the coffee and send a mail before delivering the coffee to the office. So one thing that you note here, we don't care about the decoration because even though the tasks are somewhat related, but it could be independent as well. So here you're getting the coffee. So one path would be to get the coffee, then mail it, then send a mail, and then transfer it to the office. So this path taken by the agent could be one of the way to satisfy this task and complete this goal. So we will see how are these subtasks are captured using some reward structure known as reward machine. And the second thing that the paper talks about is how to use Q learning to reach a optimal policy over reward machines itself. So we will see both of these things in detail. Yes, I've already mentioned this key contribution again and again. So first you have mentioned twice. So I would like to mention the last two, which is DPRM. So in order to work on continuous domain, they also use some deep learning methods using neural networks, and they work on continuous domain as well. And at the end, they give some results based on both discrete and continuous environments. Yes. So before even we go very formally, let's think about it as a more intuitive way about reward machine. Okay, just give me a second. Yes. So let me refresh the task which I told you beforehand. The first task was to get the coffee, avoid the decoration, and deliver it to the office. The coffee to the office. So this was a plausible path, right? So in order to capture this task, either you can have the possible set of actions which could be very different, right? Because from every state you can have four directions to go. So instead of looking at this task using these actions, we can much more simplify it and make it more compact using reward machines. As you can see, this is an automaton. So abstractly, reward machines are automaton, but the transition depends on something in the environment, state of the environment. So as an automaton, I will start from an initial state, and until and unless I get the coffee, avoiding the decoration, I both transit. So as you can see, this C and star are coming from the state names, right? So each state corresponds to a propositional symbol. So if I get the coffee, C will be assigned true. Until unless I get the coffee, C won't be true. That's why. So until unless I get the coffee and I have avoided the decoration, I will keep on staying in the initial state. And just for clarification, please for now we can avoid these numbers which are given in the tuple as the second element. I will come back to it after a few minutes. So we will just look at these transitions, the condition on the transition. So first is until unless I get a coffee, and until unless I avoid that. Sorry, till I am avoiding getting the coffee and avoiding the decoration, I will stay in U naught. As soon as I walk towards this block, as you can see, if I hit a decoration, I will reach a death state. So this is a final state in some sense, because after I reach this, I will be stuck there forever because there are no outgoing edges. Suppose not, I can reach the coffee without getting stuck by a decoration, which is this condition, satisfied by this condition. Then I will reach U1, right? So if I'm at U1, that means I have got the coffee and I have not touched any decoration. But from U1 itself, if I touch a decoration, I will again go to that state, where I will get stuck. So wherever you touch a decoration, you will get stuck in U2. And U1 denotes I have got the coffee and I have not touched any decoration yet. After that, my goal was to get the coffee, avoid the decoration, and reach the office, right? So I have done that. Now the only goal which is left is reach the office. So if I reach the office, I will reach the state U3, right? So all these conditions are over the states, right? So all these conditions which are given as predicates are over the states. So as soon as I reach U3, I will be stuck there again, right? Because there is no outgoing edge. So here, if you transit to either U2, U3, you will continue to be there. Now I will come back to the values given here. So one thing is you can see that except for this one, all the numbers are 0. Except for this tuple, the numbers in the second element of the tuple is 0. Why? So according to this reward machine, you will only get a positive reward if and only if you complete the goal completely, right? So my goal was to get the coffee, avoiding the decoration, and reach the office. So you are getting the reward 1. So here, so there are two things in this. First is some condition denoted by the states of the environment seen as a propositional symbol, and next is the reward that you will get for each transition. So that is the intuitive idea what is happening. So we can just see in this graph as well the office grid word. Suppose I'm starting from here and I followed this path. As you can see, I have touched the decoration. So according to the reward machine, I will be going to U2, right? But suppose I had followed this path and got the coffee, then I will go to U1. And suppose I follow this complete path, the full blue line, I will reach U3 as well, and I will get the reward 1. Is it clear, or there are any doubts?
Yeah, just as a comment about that. So maybe you're going to make this comment after all, but my observation was that reward machine. Yeah, I guess your motivation. Maybe I'm speaking. So it already kind of defines the intermediate tasks to achieve. Okay, first it can be viewed as an automata of that gives a specification, right? Including specification of what goal you want to achieve, and what parts where the goal is not achieved, okay, at a high level. That is one. Number two, that you can say that it kind of does decomposition of your overall goal into some tasks. And this big task is thing. Is that the idea? I mean, am I reading it correctly? Okay.
Yes. Yeah. As you can see, each of these states are corresponding to some task that you have performed, right? If you are at U1, that means you have got the coffee and avoided the decoration. So somehow it is also telling you something much more than the overall task.
Okay.
Yes. So now this is just the formal definition of it. So as you've already seen, I had an initial state denoted by U0 contained in the whole set of states. Along with that, in order to transit from one state to other, I have this function delta U, which depends not just on the state. The domain depends on both the state that where you are, and also the set of preposition that needs to be satisfied, right? So as you can see, there was some constraint here, right? So this will be only satisfied if C and star are false, irrespective of what the other values are. I don't care. Only C and star has to be false. So depending on that, so this is a cross product of the state and the truth assignment to the prepositional symbols, which are the states in the environment. And I transit to a different state. Then I have reward transition function. So this is the second element in the tuple, right? So this is this. And the second element in the tuple is the thing that you get after the transition. So as in the previous example, I have seen it was just 0 and 1, which was some constant. But you can have any function, any reward function, depending on your transition. So yeah, that is the idea. That is the idea about reward machine. So there is one intuition. I have written a block intuition. So agent will be rewarded by different reward functions at different times, right? Depending on where you are in the environment state and where you are in the reward machine, both. Yes, so propositional symbols I have already told. these corresponds to the states in the environment. So in the office grid work, I had A, B, C, D. I had coffee machines, mailing system, office, and stars, which are decoration. So the star symbol is slightly different, but this denotes the decoration. And then I have iron states and truth assignment. So these truth assignments are for the provisional symbols. And I have the state transition and reward output, which I've already explained. So here are some more examples. So I will take up this patrolling one. So we have still not used A, B, C, D, right? In some way, even though it was there. So one of our another task.
One question or comment you have. So here you've shown all the reward. In general, like in Q learning, I mean, in general, in RL, the reward functions are a function of the entire state. I mean, it just happens to be in these examples, they are constant functions, but they don't have to be, I guess, no? I mean,
correct, yes.
Okay, that is one. And you can have different reward functions at different points there, right? That is also.
Yes.
Okay.
Yes, so for the examples that we have taken and the examples that we'll discuss now also, the functions that I'm getting, that those are constant functions. So irrespective of what the state and action and what transition that you make in the environment, it doesn't matter. It will give the same reward. So these are known as simple reward machine. That's what they mentioned in the paper. But you can have any general reward function as well.
Okay, got it. Yeah, please go ahead.
Yes. So let us take this very simple example. So our another task could be patrolling from this state A, then going to B, then going to C, and then going to D in a sequence, right? So the sequence is important. So I need to go from A, B, then to C, then to D. So as you can see, this automaton, this is not very complicated. So if I'm a U naught, and I will continue to stay at U naught until and unless I reach the state A. So as soon as I reach the state A, I'll reach U1, and then.
Is there a question? Yes. By anybody? Yeah. Okay. No.
Yes. So from U1, then I will transit to U2 if I go through B, and then to U3 if I reach C, and then as soon as I reach D, this reward machine will transit to U0 and give me the reward 1. So I only get the reward 1, a positive reward, if a non-zero reward, if and only if I complete this task fully. This is one of the examples that we can see. So yeah, so there's something more that this reward machine is capturing. Instead of just taking care of the state in the environment, it is able to compactify what my task is, right? So just using 4 states, I can talk about this task. And this is another example, which I had already mentioned, that you need to deliver the coffee and send a mail, and then deliver, you have to get the coffee, deliver the mail, and then send that, deliver the coffee to the office. So here again, there are 2 ways to do it. Either you get the coffee, send a mail, either you send a mail, then get the coffee, and then deliver to the office. So there are 2 ways to reach the office. So let me just explain this briefly. So when you are state at U0, the initial state, you will continue to stay there until unless you get the coffee or send a mail. So if you send a mail, you reach U1. Sorry, if you get the coffee, you reach U1, or if you send the mail, you reach the state U2, and then you do the corresponding thing which I've drawn in this tree-like structure. So after getting the coffee, if you send the mail, you reach U3, or you send the mail and get the coffee, you reach state U3, and from there you reach the office. So as soon as you reach the office, you reach the state U3, you get the reward 1, and except that everywhere the rewards are 0. So these are like few examples related to this office grid work. I hope the structure of reward machine is clear. If there are any doubts, I can take it up now.
Any questions from the audience?
Does this not limit the exploration part of the thing? Because like we are giving it like small subtasks sort of thing, right?
Sorry, please could you repeat your question, please?
If the only goal was to maximize the reward over like a long period of time, like it would explore more than what it would do when we are giving it like small subtasks in which it has to qualify some specification, right?
Right. Even though these are like multiple small subtasks, but we are going to learn through our actions in the environment over all these states in all the reward machines. So when we'll come to algorithm, you will see for whatever action that you perform in the environment, we will going to learn through that action in all of the reward machine that I have. So each reward machine corresponds to a task, right? So these are subtasks. Each reward machine corresponds to a subtask, and we're going to learn for each of these subtasks. Shobit, does that answer your question? Or
Yeah. I was just wondering if it limits the exploration feature of like how like one of the things is like, oh, it can
no,
explore
this
a lot
doesn't,
of.
because actually we will, in the algorithm itself, we will see we again use epsilon greedy method, but whatever action that we perform, using that action, I'm going to learn for each of the reward machine again. So yeah.
Okay, yeah.
So if I understand your answer, I mean, his question was if this somehow limits the traditional Q-learning exploration. So your answer is no. If anything, it enhances, and how it is going to be done, I guess you will. I mean, I know that it is decomposing into the tasks, and how exactly this reward machine is going to be integrated with Q-learning is yet to be explained, I presume. Correct?
Yes.
Yeah, and maybe that when you do that, it maybe gets answered, and maybe Shobit, you can ask that question again if it is not satisfactorily answered. Okay.
Yeah.
Okay, so if there are no more questions, let me move forward. So now we have already defined the structure reward machine. Now we want to incorporate this in our Markovian decision process. So our environment, right, which has my state, action, the transition function using the probabilities, and the discount factor. So how we are going to connect this reward machine with this MDP is using the function L, right? So L is the labeling function. So as I've already mentioned here, all these states are somehow using some formula based on the preparational symbols depending on the state of the environment, right? So for each state in the environment, I'm associating some truth assignment to these preparational symbols. So this L is a function from the set of states of the environment to some truth assignment, right? So I've written as well truth assignment to the propositional symbols, right? So that's how we are going to connect this MDP with RM. So this will control our transition in the reward machines. And except that all these notations are similar to reward machine, I have the set of states in the reward machine. Initial state, this is the reward transition function, and this is the state transition function. And this P, this mathcal P, is the set of propositional symbols, which is basically the set of states in my environment.
But almost you're taking a cross product, isn't it? Of
yes.
The MDP and the RM, and with the label as the connecting, the labeling function that is used, isn't it?
Yes, but when we see this as this tuple, we are seeing them as a separate entity also, but we can also see them as a cross product. So if we see them as a cross product, maybe it's slightly early, this will become the rewards will become Markovian. But if we just see this as a tuple and we are transiting over this S, just seeing this, getting the reward over this S, then this will become non-Markovian. So seeing this as this tuple, this is not a direct product right now.
Okay.
Yes. Okay, so maybe let me just clarify it here instead of showing that slide, which has a lot more notation. Right, so if I'm at state S, small s, in my environment, and I perform the action A, and I reach the state S prime, right? So how would I transit in my reward machine? So for that, because I've made the transition S prime, so associated to this, there's a propositional symbol. There's a truth assignment for each of the propositional symbol, right? So that is L of S prime. So using this, I'm going to use delta U, the transition, right? So suppose I was at U, then I will transit using this. So let me write here, U goes to some U prime using the function delta U and this truth assignments, right? So what was delta U actually? Let me just mention it also. It was from the domain U cross 2 power P, which is a truth assignment to some state, right? So it will go from U to U prime using the truth assignment assigned by the state S prime of the environment. Now I want to get the reward as well, right? So what was reward function? Sorry, reward transition function. It just takes the transition that I made from U to U prime and returns me a reward function, which is of this form, right? Right. So delta R U comma U prime will give me some reward function. Let me call it R. Now, unless I stay at U prime, my reward will be captured by this reward function R. In my previous examples, all of these reward functions were constant. So that's what I have mentioned here, and I've explained it now. So are there any doubts regarding this transition in both the reward machine alongside the environment?
Yeah, maybe you can, yeah. So go ahead. I don't know if you want to answer. I mean, how does, okay, you showed this MDPRM. Is that now your original environment will be replaced by this environment, and that's what you'll be using the exploration on? The agent will be exploring on. So maybe
yeah, so I'm still exploring in the original environment itself. Just the reward machines are capturing what kind of task I'm performing and where am I in that particular task, at what level.
Okay. So you're
Yes.
kind
So
of
maybe
exploring that while you're also keeping track of this reward transitions, reward machine transitions, to figure out what is the reward function that you have to apply during exploration. Huh?
yes. So these reward machines just capture like what I've performed till now. It's somewhat like a history. That's why whenever these rewards are considered taking this environment is taken over S, this becomes non-Markovian because these reward machines are somehow holding history. And so this is something much more that I have just compared to the
That's why you're
normal
keeping
RL.
it separately. I understand.
Yes.
That point. Yes. Yeah.
Yes.
So each reward function, although they're different, they will still be Markovian because they are only using the other state. Yeah. Yeah.
Yes. Yes. So I believe like I already explained this transition, but let me just do it much more briefly. So if I were at this triangle, I have to start with this triangle, right? Yes. Suppose I had reached till the coffee. So reaching this state, reaching the state from this triangle to that C, the truth assignment for C will become true. As soon as it becomes true, I will transit from my initial state U0 to U1, right? That's all. And after that, from this C, if I perform some actions using which I reach the state O. So as soon as I reach the state O, using the labeling function, I can assign true to the provisional symbol associated to office. As soon as that becomes true, so this will be satisfied. This formula will be satisfied. I can transit from U1 to U3. That's all. That's the idea. And for every transition, I have a reward function which will give me the rewards. And we will see how we're using this reward function to calculate the Q value functions in the algorithm itself. Any questions?
Yeah, Shobit, is it your question a little bit clearer now? Or
I'm not sure,
yeah,
but
okay. Yeah. Let him see how he updates the Q table. Maybe that'll be clear then, yeah?
Yeah. Yes. So now we will just talk about in how does the policy here differs, right? So it's somewhat same, just my policy is action. In the general RL setting, we have we have the policy that I will take this action given I'm at this state, right? But now seeing this as a product automaton S cross U, my policy will look like this. Taking the action given that I'm currently at S and S in the environment and U is some state in the reward machine, right? So if I want to what is the probability that I will transit from S comma U to S prime comma U prime, taking the action A with the probability by which I will do this transition is given by this. So this is just the same probability as the original probability transition I had for the environment. We just need to ensure that this transition is valid from U to U prime. If this transition is valid in the reward machine, then the probability will be just same as transiting from S to S prime using the action A, and otherwise it's 0. So that's all. Yeah. So just we need to ensure that this transition from U to U prime is valid using this labeling function of S prime, the transition. That's all. Now, before I move to QRM, I would like to just confirm if some structure about reward machine is understood or not. Okay, so I hope it is somewhat
Yeah,
clear.
I think it's clear, but how I think you will get to how exactly. I understand how the reward machine kind of switches and how you're using that to switch from one reward function to another one at significant milestones. Okay, by connecting the label and so on. What is still not clear to me, which I think you will probably do, let me know, that, in the QRM algorithm, whether you keep the same Q table or not. I mean, this is somewhat little bit similar to, no, I wouldn't say exactly, but in terms of goal, maybe it is similar to having different predicates that, Vijayan showed that in that paper that he had, somewhat it's kind of the notion is the same thing. So I'd be interested. I think the QRM algorithm, I hope, will describe how exactly you will be using all this information in updating the Q table and integrating with the learning process. Huh?
Yes, yes.
Okay.
Yes. So before I even
Hello, sir. Just a request.
Yes, you
Sir,
have
can you see the chat? Can you see the chat once?
Oh, chat. Let me see. Please. No problem.
Sorry, sir. Yeah, like I'll just come back in 30 minutes.
No problem at all.
Thank you, sir.
Yeah. Yeah, go ahead.
yes, thank you. So yeah, before even we start with this QRM algorithm, I need to mention few things. First is I'm defining Q value function for each RM state. So if I have suppose n RM machines and each has some number of states, for each state of the RM, I'm defining one Q value function, which I'm going to learn. So I will learn some sub policy for each of these Q values associated to each state, right? That's all. So this is the function that I will talk about. U is the state of some RM, and its domain is the state and the action that it will perform. And we will see how we can learn this parallelly as well, as I have mentioned here. Oh, sorry for the spelling mistake. Right. So for this QRM algorithm, we have few inputs. So this is similar to what we have seen in the tuple, that MDPRM. So you have the set of propositions. I have the environment itself, which I've not mentioned yet, but that is also there. I have the labeling function, discount factor for the Bellman equation, which we'll see in the algorithm, and the set of tasks. Right. So these set of tasks are somehow captured by the reward machine. So which is contained in the set sigma. So sigma, it just denotes the ith reward machine. Sorry, just give me a minute. Yeah. So just
each task is represented by a reward machine. Is
yes,
it? Yeah.
Yes.
Okay.
So yeah. So we have somehow decomposed these the major tasks into subtasks, and each of these subtasks are captured by a reward machine. Yes. So as we've already seen in the office grid work, we had multiple tasks, right? So suppose there are 3 tasks, and for each task, I have made a reward machine. So suppose the reward machine has these many states, 4, 4, and 5. So how many Q value function I will update? I will have 8 plus 5. I will have 13 Q value function that I will update through my algorithm. I'm not showing you the algorithm, just giving a brief that how will I going to work. So I've got the input and how many Q value function I will be updating on making a table for. So okay,
why 4, 4, and 5? I didn't get that.
Okay, sorry. So 4, 4, and 5 are the states in the number of states in the reward machine corresponding to T0, T1, and T2. Yes.
Agent learns Q values of RM states.
So for each state of each RM, I have a Q value function for each state of the RM.
Which is pretty much like having multiple one Q table, one Q function for every RM. Huh?
Sorry, please could you repeat? Having Q table for
each state in each RM. Huh?
Yeah, for each state of each RM, I am having one Q value function, which I am updating.
Yes. Okay.
Yes. So in total for our example, we will have 13 Q value function, which I will update.
Yeah, see, that's why I was drawing the parallel between that and the waypoint RL. Algorithm that Vijayan thing. I mean, they are, although the structure is not there in the way that in the waypoint RL, here they are kind of connected, into tasks. So,
yeah.
So you are using multiple Q tables. Yeah.
Yes, there are multiple Q tables.
Mm.
So yes, I have explained this. So yeah, let me show you the algorithm, but I will first give you a brief. So this input I have already explained, like what are the inputs? Sorry. Yes. Now, for each state of each RM, I have defined a Q value function, and each of these Q value functions I have stored in this Q tilde. Right. So this is the initialization process to store the Q value function. Now, in this algorithm, I have 3 loops. So I will mention briefly what do they do, and then I will go over the algorithm one by one. So the outermost loop, this one, starting at 2, it fixes the reward machine I am going to work on right now. So it fixes the RM. Right. So I can have n subtasks, and for each subtask, I have a reward machine. So for each reward machine, there's an associated index. So this will help me to fix that index and work on it. So after fixing the RM, just give me a sec. Sorry. Yes. After fixing that RM, I'm going to okay. Sorry. Okay, I think I missed a very big point right now. Yes, let me mention it here. Yes. So it was not specifically mentioned in the paper, but Arpan helped me to get that. So the thing is, for each reward machine, I calculate an optimal policy. So it's not the optimal policy for the overall task. It's just for each reward machine. I calculate the optimal policy. And this is important for the second loop where I stopped, right? So Arpan helped me to clarify this doubt that before even starting this QRM algorithm, for each reward machine, I am finding the optimal policy for that task, right? So for this, I will have the cross product S times S cross UI, where I is the reward machine I'm working on. So before even starting this algorithm, I will find some optimal policy for each of the RM. And this is important, as we will see. So the first.
But I have one question here.
Yeah.
I mean, I know if it is a sequential task 1 after task 2 after task 3, then you can separately do this kind of policy computation. In one of the things you showed, there was a branching in all the task, and then you were merging it. How can you compute the policy separately?
Yeah, so while computing the optimal policy, you just focus on that RM machine. You just don't care what are the things about other tasks. You just care about that RM machine. So for that RM machine, you're calculating the optimal policy.
Oh, but I thought in that thing you were not mixing to reward machine. Oh, no. Okay. No. So it means these tasks are sequential then. That's it. It is not like you do part of one reward machine, then you do part of the other machine. That kind of a thing is not possible. You can't mix.
But we will see in QRM, for whatever action I perform for a specific reward machine, I'm going to use that experience to learn more about the other reward machine as well. We will see that would be the innermost loop that we are going to do. So before even starting this algorithm, where we were actually updating the Q value functions, I'm finding an optimal policy for each of the reward machines, seeing them separately. Just separately. We just don't care about other reward machines.
Okay. So then you will do something. Okay. Yeah.
Yes. After that, we're going to use this information to learn something more about other reward machines.
I got it. Sorry. Yeah. So you treat them separately, compute policies, and then you somehow merge them. Yeah.
Yes. Right. Yes. So first you fix the RM, and I've already mentioned I already have some optimal policy for just for this RM, right? So using this, my second loop. Sorry. In my second loop, using this optimal policy, I'm going to take some action using epsilon greedy method. So it's here. Let me show line number 8 and 9. So using that optimal policy, I will take an action and reach the state S prime. So I will do this some number of times, which is not fixed, which was, I think, not specifically mentioned. Like how many times we're going to do depends on the implementation. So in the second loop, I will perform action, fix the RM, suppose I, perform action using optimal policy of ith RM till sometime. That sometime depends on the number of times I am doing the iteration in the second loop, which is the middle loop, right? Now, as you can see, for each iteration in the middle loop, I gain experience, right? So that experience would be from the state S, I'm performing action A, and I'm reaching some state S prime in the environment. So this S and S prime are from the environment. These are not the states of the reward machine. So after this has been fixed, so let me write it more hierarchically. This has been fixed. The innermost loop will take this experience and will update the Q value functions for all the state of all the reward machines. It's just not the Q value function of the reward machine I'm currently at. It will update the Q value function for all the reward machine using this experience. So I will just write it, update Q value function for all states of all RM using the experience that it has gained in one iteration of the second loop, the middle loop. Right. So let me just go over this algorithm one by one. So the outermost loop talks about it fixes the RM, right? So it will fix the RM by getting that index I. After that, fixing that index I, it will start from the initial state of the reward machine, ith reward machine, and in the environment itself, it will start from the initial state of the environment, depending on the environment. After this has been fixed, now I will go to the second iteration where I will perform some action using the optimal policy of the ith RM, right? So that's what I'm doing. Until and unless it's the dead end, so where there no action possible in that specific state I'm currently at of the environment, I will continue performing some action using the epsilon greedy method and go to S prime. Now, once this experience is fixed, my experience is what? Going from S to S prime using the action A. After that, I will use this experience to learn to update the Q value function for each state of all RMs, right? So this Q naught J belongs to Q tilde. Q tilde has all the Q value functions which I'm going to update. So this update function, so I will make some transition. Sorry. Just give me. Yes, right. So in the Q value function, I'm going to update the in the innermost loop, I'm going to update the Q value functions. As you can see, until this is the dead end, I will just update by this. Otherwise, I will use Bellman equation and update the Q value function for that state S and A, right? So my experience was fixed. So that is the important thing. My experience was fixed for the innermost loop. So I will update the Q value function for that specific input. And after this has been done, the innermost loop is over. I will make some transition.
I didn't quite understand the line 13, 14. What is environment dead end? And there you're not using Bellman equation. Why not? Why? You don't need to. So in line
yes, okay. The thing is, in the Bellman equation, I maximize over the all possible other actions, right? But there are no other action possible from S prime because it's a dead end.
It's a dead end. Okay.
Yes, it is actually Bellman equation, but that would be just 0.
Okay.
Yes, rest of the term was just 0. That's all.
No.
Yes. So as soon as I leave this innermost loop, I'm again back to the middle loop where I will do the transition in both the reward machine and the state of the environment. But here the reward machine is the reward machine which was fixed by the outermost loop, right? So as you can see, this I corresponds to the outermost loop. So I will just do the transition here accordingly as seen here. So whatever experience that you gain for through a specific reward machine's optimal policy, you're going to update the Q value function for all the states of all the RMs. So somehow you're using the experience from a specific reward machine to update the things for everything. So that is the idea. Any doubts, any questions here?
Yeah, I mean, Shobit, you asked,
I mean, since Vardhan said that we are still using the epsilon greedy method, and I think it's, I don't know how it's enhancing, but it's at least the same, right? Like we aren't doing anything.
here. But one question I had was, I mean, I know you're doing it in this loop and so on. But why? Once again, these tasks are intermingled, or I mean, I know that shouldn't you have some kind of a way of is the main task somehow a simple composition of the? I mean, doesn't the main task, which I presume is going to be, if the main task is going to be which the policy has to be learned, is some composition of these individual tasks for which you have a separate RM, correct?
Yes, yes.
Now, shouldn't the way you do the learning process by exploring the environment, by doing the process, be dependent on the structure of that composition? You know, I mean, I'm saying, let's suppose I don't know what the structure of your how the task is composed. So let's suppose that I say, oh, if it's a if then else comes in, if some state satisfies some condition, then go according to RM, task 1. Otherwise, you do task 2, and then you do you merge, and then you do task 3. Then you split. I mean, are those kinds of things possible? And if so, will this be consistent with that dependency among the tasks in which I'm saying that if the task composition is somehow state dependent, will this work? That is the question that I'm raising.
Okay. So I see one of the example that they have given is that whatever the exploration a specific reward machine does, it helps us to get information about other reward machine, like what will happen to other reward machine. So somehow it's able to learn faster. That was that they have said, or maybe I have not understood your question well. Maybe you are saying like if the tasks are completely independent, so this won't help, right? Somewhat you can just do it
I
independently.
see this can work. Yeah, if they're very interdependent, then I'm not sure if it will work or not. That is the question I'm raising.
Okay. I see. Okay, let me just take the because I'm also not sure how to answer
the
that.
question that I've raised. I think you should continue with your the way you're presenting it, and then we will revisit it. Yeah.
Yes. So I think I've already mentioned the Q value updates, how I'm doing. It's just the Bellman equation right now. So let me just take the example. Maybe this might help with that. Right. So we had three tasks. One was T1, T0, and T2. Let me just check the task as well once more. So T0 was to deliver the coffee without breaking the decoration. T1 was patrolling ABCD, and T2 was delivering the coffee after sending the mail to the office. So I will just read through one of the paragraph that they mentioned in the paper to show how it is relevant to have this intertwining. As a concrete example, suppose that the agent is trying to solve the patrol task T1, where I'm going from ABCD and all those. While exploring the environment, it reaches the office O. And reaching this office O was not very particularly important for the patrol task, right? So reaching this office was important for task T2. However, the agent can still use it to learn how to reach the office and thus improve its performance for the delivery task. The learning loop is an implementation of this idea using QLearn.
They're kind of independent. Okay, so they don't interfere with each other is what is the point that's being made here. Is okay. But whether it will be as effective as some other, So here at least you're doing independently, and whenever one task completes, you continue with the other tasks. That's how it's being done too. Correct?
Right.
Yeah.
Yes. And one more thing, in this inner loop, as you can see, you can update this Q value functions parallelly, right? One thing which is which we can see, at least for the for all the RMs, you can update the Q value functions parallel. That is one thing which gives it that makes it more efficient as well for the innermost loop. Yes. So then they have mentioned a theorem for which the proof they have mentioned the appendix, and I have not read that. So the theorem states that given a list of MDRPMs, the Markov decision process reward machines. I think I changed the symbol. It should be MDPRM. Over the same environment, the environment is still the same. I have multiple reward machine. QRM converges to an optimal policy in the limit. So as the number of episodes goes to infinity, and the length of episodes, the number of times I am moving over the environment for the fixed reward machine. So that is what they have told. And how do they make it efficient? So I will just read this last pointer. Subtask queue function can be updated in parallel. I have already mentioned that. Apart from that, for to avoid the expensiveness of computation, instead of updating the key value function for every state of every RM, I can do it for a random subset. So this is another way to make it more efficient. Yeah. So this is the convergence guarantee, which was not there in HRL.
Oh, I see.
Yeah. And in order to work on continuous domain as well, they have talked about the topic deep QRM. So, so using deep learning techniques, they are going to find some optimal policy. But here, one very important thing that they have mentioned is there is some trade-off. You can there is no guarantee of the convergence. But the only benefit that I have, I can work on continuous domain. Yes. And one more thing, they uses a double DQN to learn subtask policy. I'm not very much aware about this technique, but that's what they use in the inner loop to learn the subtask policy. Sorry, not the inner loop, the learning the optimal policy which we learn for that. So let me, I have covered this, the convergence guarantee for QRM, and there is no convergence guarantee when you have the continuous domain and when you want to use the deep QRM.
Yeah.
Yeah. So maybe I can take some questions now before going to the next section of experiments.
Yeah. Diganta, still there? I mean, because he had raised some questions about convergence, although they were with respect to a Markovian thing. Because here the reward functions are individually Markovian. But I guess why I was going to ask, so since the convergence question, that's why I was deferring to him. Why would convergence be lost if you move to deep, if you represent Q functions as DNN because of continuous, because they are.
It's also because of the technique they're using to learn the subtask policy, at least what they mentioned in the paper. I'm just reiterating that.
Okay.
Because the technique they're using to get the subtask policy, that itself does not help you that much to get the convergence. Yeah, but even in the paper, they have mentioned this deep QRM very briefly, not in much detail.
Okay.
Yeah.
So are there any questions from people? Okay, let's move on. Yeah.
Yes. So let's come back to results and implementation that they have done. So briefly, I will tell you. So they perform this evaluation on both discrete and continuous domain. And there are few questions that they want to investigate. First of all, is they want to improve the efficiency. So for that, does using off policy RL to learn subtask in parallel improve sample efficiency? So by off policy, I mean we mean that we are training while doing the training, we also take the information of some other experience, right? So as we have seen in the innermost loop, even though their experience was for that reward machine, for that transition of that reward machine, we were using that experience to train the Q value, to update the Q value function for other reward machines as well, states of other reward machine as well. And the second question that I want to ask is, does task decomposition help DQRM or QRM to find better policies than alternatives HRL methods, which I already mentioned in the beginning? And it does. We will see that. So for the baseline, so in order to compare this current algorithm, the current implementation, they have fixed some baselines. They have taken the baseline as double DQN, then HRL, which they have talked about, and HRL. Yeah. Any question?
No, I think it was just some noise.
Yeah. So in order to compare, they have taken three baseline. One is double DQN, HRL, and HRL with RM-based pruning. I'm still not very sure about the third one though, like what do they mean? But yeah, these are the three baselines that they have taken. And to compare this, they have worked on three domains. So the first two domains are discrete. So these two domains are discrete. And the last one is continuous. So one of the discrete domain we have already talked about is the office grid word, which we have already seen. And in order to compare this, they've normalized the discounted reward and they check the median and interquartile range. So these are the metrics to compare these from these other methods of reinforcement learning. So maybe I'll show you the results first. Yes, so this is for the discrete domains. This first one is for office word. So what do they do? After some, okay, let me just specify how do they get this graph itself. So let's focus on this last pointer. So after every n step, they evaluate the average performance. So this n depends on what kind of domain you are, either discrete or continuous. So after these n intervals, they're calculating the average performance across the task and they normalize it by maximum discounted return that you can get. And then they're plotting the graph. That's all. For each interval, you are doing the average performance across the task. That's all. So here, as you can see, red one denotes the current thing that we already talked about, QRM, red one. And the purple one, the lowermost one, is the normal Q learning that we use. As you can see in the B, for the Minecraft word, it's Q learning is not at all useful, but QRM is really great and it's much better than other baselines that we have fixed, HRL and HRL RM as well.
So they're just comparing the cumulative reward in each cases, huh?
Yes. They're just averaging out the cumulative reward in each interval and then they're talking about it. This is for the discrete domain. And let me show you for the continuous domain. This is the water word domain, which is the continuous domain. Here also, the deep, I think I have made some mistake while writing it. Yeah, so the double DQN, let me just check it once, the spelling. Yes, the double DQN is performing very badly in this way. It's the lowermost portions of the graph, while DQRM outbeats other baselines, suppose DHRL and DHRL RM. So as you can see, this D denotes the deep learning methods that they've used to work on the continuous domain. And why it's continuous? So in this, at least in this example of the water word, as you can see, if you're at this position, at this state, you can move in any of the directions. So as you can see, it's a continuous, the set of action is from the infinite space. It's not finite. That is the thing. So let me talk about it briefly about discrete domains. Yes. So I already mentioned they compared this on two domains, office word and Minecraft. And for this, they specified the hyperparameters as this learning rate, discount rate, and epsilon for the epsilon greedy method. And for the continuous domain, so let me just inform you about the environment. How does the environment look? So it's a 2D box with bouncing colored balls and a white agent ball. The agent can change velocity in 4 directions, enabling complex movement. Task, touching ball of a specific color in order. So I need to touch the ball in a specific order. Okay. I think I'm really sorry. I think I made a mistake in specifying the action. My action is with a fixed velocity, I can go in any of the 4 directions. But what velocity, that I don't know. So I think that is the infinite domain, not the direction I need to go. Sorry for that. Yes, so that will make the domain continuous, the set of action continuous. Yes, these are some other details related to the experiments. But yeah, so majorly we should focus on this graph, which captures how Q learning using the reward machine outbeats other baselines. Maybe I can take some questions now if there are any.
Any questions? No, please go ahead. Yeah.
Okay, so these were the experiments. Now I'm kind of at the end of my presentation. Yeah. So I will just summarize what we have seen. So this is the key outcomes of the experiment, which I've already explained. So let me just come back to sample efficiency. So as you can see, This performs much better because it's able to avoid the local optima captured by HRL. That's why in all of the cases, it was able to outbeat HRL. So this yellow line is the HRL and red one is the QRL. Yes, so the summary, we introduced reward machine for structured reward decomposition, developed QRM with provable convergence in the tabular case for the discrete domains. Let me specify that. And it was extended to continuous domain using DQRM. And okay, let me read the last point as well. Highlighted advantages over HRL and flat Q learning in sample efficiency and generalization. So in few of the cases, we have already seen the Q learning did not give much return, right? So in few of the cases, I think that even in this case, it was quite flat. And even for this Minecraft word domain, the reward gained by Q learning was absolutely nothing, 0. Yes. So in the future work, at least one thing which I am very interested in is how to make all these reward machine, right? So we already talked about reward machine, how to automatically synthesize these reward machine in order to actually implement this algorithm, because we need the reward machine to use this algorithm. And another future work could be integration with external memory and mapping between formal languages. So how is this relevant? In the sense, reward machines are kind of automaton, right? So they are somehow related to some language. So I have not mentioned that very even briefly, but each reward machine can be each reward machine is associated to some truth assignment to the propositional symbol, right? So these can also be seen as regular expression over the states of the environment, because this will denote the truth assignment of the. It will give you the some label of the state. So we can also see associate languages to the reward machine. So that's all they want to talk about in the third one, mapping between formal languages and reward machines, and extend it to multi-agent. So currently we were in an environment where multiple states and multiple action, but only one agent was performing that action. So we can have that as well. We can have that extension as well. Yes. Any questions?
Yeah, I think with respect to your future work, the things, looking at LTL and this combination, I think some people have already worked on that. Using reward machine. Well, I don't know. I mean, there's some overlap in that thing. So the second.
So sorry, go ahead. No, I was going to say that I have some questions, but go ahead. I'll just ask anything.
No, you please do ask the questions. This second bullet. Is it just an implementation thing, or what do you mean by integration with the external memory, LSTM? Is it just an to improve efficiency of implementation, or is some functionality being enhanced?
Yes, at least to my knowledge, I think it's implementation, because one of their major goal was also to improve the efficiency of the algorithm overall.
Yeah. Yeah. Okay. Good presentation. I mean, I like the thing. Thank you. Yeah. And
it was. Yeah. So first question that I want to ask is, so you're comparing it with flat Q learning, right? But I mean, these kinds of compound tasks are not even expressible in flat Q learning, right?
Yes, that's why. Yes.
No. Can you bring up this one? Yeah, this one as well as the next one. Okay. So what are the various things that you complain? Maybe if you could summarize that will partly might address his thing. I think you're comparing with HRL, and what are the other ones? What is yellow? What is blue? What is red? And there is more colors in the other one, no?
Yes, somewhat the purple one is denoting the Q learning, yellow one is denoting HRL, the light bluish is denoting HRL RM. I think it's related to some pruning and stuff. And red one is a QRM, the thing which we talked about in the paper itself.
Yeah, so the blue is basic vanilla Q learning. HR is some formalism attempting at hierarchical RL. How exactly it works, you didn't. I mean, yeah, it was not part of your within the scope of your presentation, but it doesn't give any guarantee. What is HRL RM? That's another one.
Yes, let me come back to that as well. This is HRL with RM based pruning. So Prune's option, irrelevant to reward machine transition, aims to reduce search space and guide exploration. So even though I have written this, but I'm not very sure, as I told while presenting this as well, at least for the third point, I'm not really sure like what they have done.
Okay.
Right, and it's not
Given
very
this information, go ahead and ask, follow up your questions.
Yeah. I mean, see, HRL and HRL RM. I mean, I understand that you would be able to express these kinds of tasks, but like if you have a task like okay, fetch coffee, then do something else, and so on, that is just not even expressible as a reward in a normal MDP setting. So, normal vanilla queue learning will not even be able to understand that task
why do you say
specification in
that?
the first place, right?
But why do you? No. I think if correct me if I'm wrong. No, you could flatten the specification also. You could say just go.
I mean,
I know
so
that
we would have to design a reward policy. I mean, I might be wrong, but we would have to design a reward function that will be maximum when it follows the path that we want it to follow in the reward machine, right?
That's true. But okay, I will let
sure.
answer it. But one thing that I wanted to draw attention to, see these Atari games, etc. They have lots and lots of intermediate milestones. They go into this 1 door, 2 door. You'll have to go into one world, and then you end up you have to solve a whole bunch of things before you go to the next world, and so on. So there, I'm not sure how exactly that's a very complicated accumulated task. No, I mean they all probably do by flattened reward machine structure. I don't know.
I don't know. I mean,
that's a good point.
They might, but but that I think there is a couple of things that helps. Typically in these games, although there is this kind of sequential things, in a number of these games you do have a very explicit score readout as well, which is going to, generally speaking, increase as you keep making progress. And I think the models, even if they're not explicitly, they implicitly learn to exploit that to a certain extent. In that case, so I think that is why there one may not need the part of this reward machine. My question is, I mean, if I want the model to say and then say do something else, about what second task was in the example, go to A and then B, how do I write that as a reward function, right? I mean, if model is it itself is visited A or visited first, because you can just keep that.
You're breaking up, Digantap.
Hello.
You're breaking up.
Yeah. Okay. So one thing is,
I think in the meantime, since we heard part of your original thing, can you address this question? First part of his thing. How can you even? His question was, could you, they compare it with vanilla Q learning. Could this how are they able even to express the reward machine there? Are you able to answer that, Vardhan?
No, sorry, I think I have not explored. They have mentioned few papers regarding this that I need to explore. I have not done that, so I don't think I can answer that clearly.
So one thing, if I can say, so since this reward machine, if you want to flatten the task, I mean, if you want to use the vanilla queue learning, you have to give some reward for the intermediate task also.
Yeah.
Otherwise, that is not possible.
Yeah, which means how exactly will you do that? Which means that the reward function definition will be very complex. No, all these predicates that they're using will have to go into the logic of defining the reward function. That is one way I could think of.
Yes, but another important thing is you have to, normalize the path length. So because since if you have to give some positive reward, because you're not using reward machine, you have to give some positive rewards to the intermediate milestones. So the rewards, what the reward machine, what the RL can do is visit that state over and over again, and gain the profit multiple times,
and then try the
yeah. So one thing actually is normalize with the path length. Once you normalize it, you're trying to reach the goal and maximize the profit using the smallest path length possible. That is your goal. If you really want to use vanilla Q-learning, that's how it should be. But
I
even
see,
then,
I see, I see. But yeah, that will probably not be able to exactly capture our intent directly, and there'll be some way of giving it some one way or another, right?
yes, yes, yes. But that doesn't perform very well in practice.
Mhm.
Yeah, so that was, I guess, the
I think
question
in
that I
theory,
had. The other question I had is, yeah. No, go ahead.
No. I was just going to add, I think you're right. It is not that it is not possible to express it. Maybe you can embed all these things, information about the intermediate milestone, etc., in the reward function and making it complex. But it is quite, you won't be able to even express it as effectively as these kinds of languages, because here you're using a powerful language, no? The automata language.
Yeah.
Do that. Yeah.
Yeah, and I'm not even sure if always we can express it in a, like, we can design the normalization in a way that the minimum reward or the maximum reward obtained is exactly when we want it to be, like when the particular like one task after another is performed in sequence only, and then and only then is the maximum reward obtained. I was thinking whether that is always possible or not, but I guess that's a question for a separate time. So I had another question, which is that so when we're dividing it into sub policies, do we need to do that? I mean, if the reward machine state that we are in, if that is already visible to the policy anyway, can we not simply train a policy that looks at the state we are in and the reward machine state we are in, the sort of propositional variable valuations we have at this moment, and based on that decides what it needs to do? Is that not directly possible?
I think yes, but then you have to take the cross product of all the reward machines.
I'd like Vardhan to take a crack first, and then you can add that.
Yeah.
Vardhan,
Yes.
did you hear the question?
Hello. Yeah. So just to clarify the question, like instead of just fixing an RM and taking the environment, instead of finding the optimal policy for that, why shouldn't I do it for a given state and a given state of an RM, right?
Yeah, I mean, as in, why do we need sub policies like one for each state of the reward machine? Why can we not have just one single policy which looks at what state of the MDP and what state of the reward machine I am in, and simply just makes a decision based on that,
Yeah,
right?
it is like pretty much saying, why don't you make the state of the environment now as a cross product of delta? I mean, the reward machine and the thing. I think you might have answered that question. No? Then I think there was some. Okay, why don't you go ahead and answer that? So you said something.
Maybe I missed it if that was mentioned somewhere.
No. I think I might be interpreting. Go ahead, Vardhan. So what happens? I did ask that question. Okay, why not take the entire environment state as environment as your MDPRM, and where the state is delta. I mean the reward machine cross the original environment state.
Right. Okay. I'm not absolutely sure that I can answer this fully, but one thing I know in terms of efficiency, at least, working on individual state of the RM helps you to learn parallelly. At least that is the one reason could be this. I'm not sure exactly the actual reason that could be there, but yeah.
No, but didn't you say that this, if you kind of do delta cross S, you RM cross the original environment, your reward function may not be Markovian anymore?
Yeah, if you just work on that tuple which I had already shown. So if you are getting the reward over S, then it will be non-Markovian. But if it's on the cross product, it will become Markovian.
Yeah, it is Markovian. Oh, okay.
Yes.
So they could do that, but I don't know. Then you will lose the structural this thing. I mean, you're merging everything into Q table. I guess there'll be one Q table then. There'll not be multiple Q tables, right?
Yes.
I guess you could do that in principle. Yeah.
I think we can do that. So I think at least the motivation that I see is maybe efficiency, because that they have mentioned it multiple times, the word efficiency, for some reason.
Yeah, I mean that makes sense, but I would imagine that even if you have a single big policy on the product space, you would be able to train that policy parallelly across multiple playouts and so on. And but yeah, perhaps that will not be as clean as this. Yeah, maybe that makes sense.
Won't you be losing some advantages of decomposition. I mean, you can now
Yes.
train
Yeah,
that.
yeah. I mean, yeah, now the policy is strictly more expressive than it needs to be. Yeah, I guess. Yeah.
Yeah, their task is to perform for a single task. Their plan is to get the optimal policy first, then use that information to train the other optimal policies to make it much more efficient, I guess. Because if you take
Okay.
the cross product, then it loses the priority of this task, right? Then it is a global thing. They want to have the
I see.
local
I
thing
see. I see.
maximized also use that local maxima to train for the global maxima, not the other way around.
Okay, okay, that actually makes sense. Okay, so for example, in this case, just going from U0 to U1 is something that they'll sort of optimize to the best of their extent first, and
Yes,
then they'll use that to sample paths when they try to train for the U1 to U3 edge, something like that. You're saying, right?
yes, something like that. Yeah.
Okay, okay, that makes a lot of sense. Yeah,
Okay.
yeah. I think that's all the questions I had. Yeah.
Good. Thank you. Any other questions from anybody else? Arpan or anybody that have?
For me, it's fine. Yeah.
So thank you very much, Vardhan.
Thank you so much.
A good talk. And yeah, Shobit, I mean, if you could stop sharing, I will let.
Yeah, I'll share. Is Shaurya there?
Yeah, you can share it now. Thank you all for putting up with another long day.
Right, you can see my screen.
Yes.
Yeah, okay. Yeah, so my topic is safe
Shauryam
reinforcement
is here,
learning.
no? Shauryam?
Yes, I had to plug
Okay,
in
thank you. Yeah.
headphones. It was not working.
Yeah.
Safe reinforcement learning via shielding. Right, so I was planning to introduce what reinforcement learning and Markov synthesis is, but I assume that by now everyone has a general idea. So should I skip this and should I come to the safety part?
I mean, if it is in your flow of thought, you can do it. Yeah.
Sure, yeah. Like Markov decision process that we see now, it's a tuple. S is a finite set of states where there is an initial state, and for every state there are some set of actions that they can take with the probability with some probability, and then for every time from S to, if you take action A and you land in S dash, there is a reward function for that. There is a reward function that maps this S dash to a reward, and the goal of the agent is to maximize the reward. So we usually design the reward system in such a way that by maximizing reward, things that we want happen, sort of, right? So over time, it tries to maximize expected cumulative reward. The gamma k, it's a discount factor, because so usually what happens is, like, the agent, if we want it to be more, we want it to get more bang for its buck during the initial phases of exploration, and then as it explores deep and deep, the reward actually, like, diminishes down. And then after the exploration phase, it comes up with the optimal policy pi. So the optimal policy is the set of states that it's mapping the states to actions. So what states, what actions it needs to follow to maximize its reward. Right? So why safety is important in RL? That's because all the actions, they are probabilistic, even though they're probabilistic, even though they are not in the optimal policy. Sometimes they can happen, and during the exploration phases, agents can explore things that can cause critical damage to the to the system. Yeah, and they can, if we haven't designed a reward function properly, they can exploit unintended loopholes. And yeah, right. So what is safety in right? Safety is not guaranteed unless it's explicitly enforced in the learning and deployment. It can be there in the optimal policy. And we'll come to how we ensure safety. It's this process called shielding, like I said. But before shielding, I want to do a few prerequisites. The first thing is linear temporal logic. So linear temporal logic basically allows to express changes in truth assignments of a formula over time. So P in T not some proposition P could and P equal to 0 could be true, and that T equals to 1 could be false, and then T equals to 2 could be true again. And this sort of change, linear temporal logic allows you to describe the change. So we use these 4 operators, and we can make multiple other operators using these 4 operators. So the basic 4 operators are next. So if we say X P is true, that means that P holds in the next state, whatever if P is. So if I say something like P equals to true and X P hold, this says that whenever P is true, it also is true in the next state, which would ultimately mean that P is true in every single state. Globally means that something, some phi holds in on every single state on the trace. Finally means that there will come some after some finite states k, there will come a point when phi holds, and phi1 until phi2 just means that phi1 will keep holding until phi2 keeps holding, right? So phi1 will be true, and until phi2 becomes true, and then phi1 will not be true, right? So these are the sort of this is the sort of logic we'll use to describe what are safe states in our system, what are not safe states in our system. The other thing that I want to introduce are safety games. So safety games are just basic automata functions, but all of the run of a safety game is within the set of final states itself. So if a trace of the safety game goes out of the final states, we say that it's not accepted. The whole thing should be inside final states. So whatever. An initial state is also in the final state. Only then it could be a safety game. If the initial state is outside the final state, then it will not. Then trivially, it'll not be a safety game.
Yeah. So safety automaton is just the negation of. It's an automaton for negation of a safety property.
Right. Yeah.
Okay.
Yeah. The third thing that I want to introduce is a 2-player alternating game. So if you guys, yeah, I assume everyone is taking POC. So a 2-player alternating game, just how it's described in the paper is a little bit different from how it's described, how I studied it in lab, or how it's described anywhere else. So you can think of automaton, which are marked some labeled 1, 2, and since it's a 2-player game, it'll be labeled either 2 or 1 or 1 or something like that. But 1 or 2 will be labeled 1 or 2, and then you can take some transitions. Suppose if you read A from here, you can go to 2, and then if you read B from, you can go to 2. And player 1 plays on all the states labeled 1, player 2 plays on all the states labeled 2. And there are some unsafe states that we don't want to explore. Player 2 tries to reach the unsafe states, while player 1 tries to be in the winning region by taking some transitions. The set of states from where player 1 can always come up with a strategy to counter B's moves, it's called the winning region. And the set of states from where no matter what player 2 does and no matter what player 1 does, player 1 will always win is called the paradise. Right? Because it doesn't even need to think about a optimal policy or optimal solution. No matter what it does, it will always remain in the winning region. It's called a paradise. It's important to see that not if there is a safe set of states, there is a safe. These are the safe vertices. Not all these vertices are winning regions because one of them can lead directly outside of the safe set. So if this is a state labeled 2, and 2 can just take a transition B out of the safe state, right? That's fine, because this is something that we'll use later. Okay. Right. So now the prerequisites are done. We'll come to what shielding is. So usually what happens is that there is an environment and there is an agent. In the traditional RL process, an agent takes some action and the environment gives it some reward. But this action could be an unsafe action. So we put a sort of screen between the environment and the agent, which somehow, if it's wrong, so there are two ways of doing it. One is called a preemptive shielding. What a preemptive shielding does is that before an agent even reaches a state S, it scans for all the actions that are available for S, A1, A2, A3, A4, AN actions, and removes all the unsafe actions available to the agent itself. So this in some way modifies the MDB to remove all the unsafe actions. This is called preemptive shielding because it works as soon as the agent reaches the state, preemptive, before even it thinks about choosing option. The other is called post.
But you may not you may not always be able to do this for LTL because, you know, as a result of taking this action now, maybe in some cases you'll be able to do it, maybe especially safety property. If your LTL property that you want to satisfy, eventually you have to get something done, I mean, something like that. Then you never know when you take this action in this state, whether this is a safe action or not. Correct?
I mean, we'll have some LTL properties that define what a safe state is, right? So if we are reaching an unsafe state, we won't take that action that makes us reach the unsafe state. So if S, should I actually?
Yeah, I think let me come back. Okay.
Right.
So when
right, okay,
go ahead. Yeah.
So preemptive shielding.
Yeah.
Preemptive shielding. So a shield computes the safe actions. So safe actions here means that actions which are reaching safe states. So if it's S1 and there are K actions, and maybe first two of them are reaching unsafe states, so it will filter out those actions and then only take the actions which can lead to the safe states, and then it will give only those actions that are safe actions to the agent to choose from.
Yeah, but this is where I had a problem. Okay.
Yeah.
I mean, yes, if you know if it's an unsafe state, if it's an invariant property,
right.
then you know whether this is unsafe or not. If my property, since you said these properties that you want, I mean, is it only safety property in the sense of LTL? Because you said the entire LTL, okay, with until twice.
So
the property that I want to ensure is okay. Some bad state will eventually never reach from this S1. How will you know here that the next one?
Bad reach. Okay, so some bad state from eventually never. So when we synthesize this shield, we'll have this thing called a look ahead, in which like it can actually look ahead and then see if we at some point will do something. So I think that's where it'll become.
Okay. So here you
little bit clear. Yeah. So there is some sort of there is some sort of look ahead that there is in the shield.
Okay.
Okay. And the agent that selects the safe actions and the environment then executes the safe actions. Right. In this, like we have fundamentally changed the MDP. So if the input was some MDP M, we have given a new MDP M dash with some actions removed, a more constraint. Right? Right. Yeah, this is preemptive shielding. Okay. The other sort of shielding, which is more preferred by the paper, is called post shielding. So in this, what happens is that it lets the agent, the shield, lets the agent pick an action 80, and only if it sees that 80 is leading to an unsafe state with respect to some specification that we have given, only then it replaces it with a safe action A-T. And then environment executes A-T, and then everything happens as it happens, as if the agent had picked A-T. Right? So here the shield is intervening only after the agent has decided an action, but the environment hasn't executed it. Sorry, it hasn't executed it. Right? So that's why It's called post shielding, and we can enhance the post shielding with letting the shield ask the agent a ranking of its next the ranking of all of the actions available. So if there are k actions available, the agent can say, oh, I prefer a5 over a6, and then I prefer a1, and then I prefer so on and so on till ak, whatever it is. And then shield will see and be like, oh, if a5 is unsafe, then remove a5 is a6 is unsafe, and find the from the topmost, find the first safe action and then execute it, right? And if all the ranked actions are unsafe, then it picks the arbitrary fallback. So once we have introduced this sort of shielding, we need to also, so there are two ways of rewarding. They're changing the reward process also a little bit. So the first way of rewarding is the punishment approach. So every time a bad unsafe action was picked, what we do is that we assign a negative punishment to it, to the unsafe action. And then agent learns that selecting this unsafe action at this state specifically is unsafe, right? So it will encourage the agent to not use the unsafe action over time. Whereas the other approach is that, oh, we have already figured out that if there was an unsafe action A1T and we can replace it with A2T, which is a safe action, then why not just let the agent pick A1T and every time we'll just replace it with A2T. So it actually gives the true reward that it would have gotten while it executed A1T, even though the actual the thing that is getting executed is A2T. Does that make sense? Yeah.
Yeah.
Okay. So the cons in both of the things are that obviously they will be needed during the exploration phase, but the problem is that since we are letting it choose uh, yeah, right. So in reward passing approach, since they're letting it choose, and we are also giving a reward for letting it choose the unsafe action, this will definitely be there in the optimal policy. And then we'll have to run this post shield during the exploration phase as well as the as well as the execution phase. Like both learning and execution phase, they should be active. And then unsafe actions are a part of optimal policy. But again, we know how to fix the unsafe actions, so we don't care about them. Right. Now, the paper claims that post shield, sorry, the paper claims that the post shielding is very advantageous, but I don't exactly see it. So these are the things that it has written as been like it is minimal intrusion and leaves the agent's choice intact. But it seems like a very subjective argument. What is, because okay, I agree that it doesn't change the MDP fundamentally, but right, yeah, it sort of does the same exact thing as.
Are you sharing your screen?
Yeah. Am I not sharing?
No.
No.
I think you went away from the moment.
Right. Right. So okay, obviously a big advantage of post shielding is that even if it's in the execution phase, even then it will work because execution phase, the agent knows it wants to choose this action and it will just change the action. But the preemptive shielding, once it has chosen action, it can't do anything. It can just restrict the state of action that it can choose. So that's one big advantage that I actually see. Yeah, that's actually right. So the main meat of the paper is how do we synthesize such a shield given a MDP, given a LTL properties that we need to follow? How do we synthesize such shield? So I'll actually go down and give a glimpse of an example and then come back up. So this is an example that we're working on in the paper. So the setup is that there's a tank and we want to train this controller of the tank when to open the inflow, when to open the outflow, and yeah. So the capacity of the tank is 100 liters. The inflow is 0 to 1, like the inflow valve, it's 0 to 1 liters per second. The water comes in. Sorry, it should be outflow. The second one should be outflow. The outflow when valve is open is 1 to 2 liters per second. And then every time you open a valve, it should be open for at least 3 seconds. And every time you close a valve, it should be closed for at least 3 seconds. What we want to do is that we want to take care of this property, that it should be at least open and closed for 3 seconds. We want to avoid overflow. We want to avoid running dry. Right? So we have come up with some LTEL specifications to do that. First, we are saying that globally levels should be greater than 0. Globally levels should be less than 100. When open turns to close, so when something is open, the next is closed. It should be closed for next 2 steps, and when closed turns to open, it should be open for next 2 steps. Right? Now, if we make a shield for this, what are the sort of things that we want out of that shield? Let's see that first. So our shield should obviously open the inflow valve when the tank level is too low. But when the tank level is too low, that it should, when the tank level is at least 4, see, since the outflow is 2 liters per second, and if it's okay, 1 second, if it's at level 4, if the tank, suppose it's 4 liters, and it opens the outflow valve, it should need to keep it open for at least 3 seconds. And if the water, if the outflow valve, the speed is 2 liters per second, in those 3 seconds, we lose 6 liters, which means our tank will run dry. So our shield needs to calculate this and then not open the outflow valve when it's below 6 liters, and also and then open an inflow valve when it's at 4, right? And then also we can't open an inflow valve when it's at 93, because our capacity is right. I think this is inflow, right? Inflow some capacity. I'll just check 1 second. I messed up the inflow and outflow numbers. Just a second. Right, the outflow is 0 to 1, and inflow is 1 to 2, right? So suppose it's at 93 liters, and we open the inflow valve, which should be open for at least 3 seconds. So in those 3 seconds, if it's like 2 liters per second, so in those 3 seconds, we'll get 99, and that's the maximum we can get. Right? So it should take care that, if it's above 93, it doesn't open an inflow valve. If it's below 4, it doesn't open the outflow valve. All the things our shield needs to take care of. So that's why somehow it needs to look ahead, that if it's so opening inflow valve at 4 directly doesn't negate the safe state, right? But it should see that if you open it here, 3 seconds later it will negate the safe state, right? So it's sort of we need to look ahead, sort of, right? Is that the same thing that you asked? Maybe. Hello, am I audible?
Yeah, you are.
Yeah.
Is there a question?
No, I'm saying it was
No,
that the
I
same
said
thing that you asked, that like this is how I am telling, like we need a shield to look ahead, because if it
Yeah.
opens the inflow valve at 94, it doesn't directly violate the safety property, but it need to look ahead that 3 seconds later it will violate the property. So that's the sort of thing that you want out of the shield. Right. So the first thing that we'll do to synthesize the shield is make an abstraction of our MDP. And this is I believe, the most difficult part. If we make a good abstraction, we can synthesize the shield. So what the abstraction of an MDP would be? So our MDP could have infinitely many states, could have a lot of billions, trillion states. we want to sort of compress the number of states. We want to only care about the crucial movements and what sort of state is it in. So like if it's a car, we want to take care of it when it's only near a cliff or it's near an intersection, then it's going to mess up that sort of thing. So what we'll do is that given an MDP, we'll make an observer function f that gives label to every state, gives some label. And then we define a safety automata, which has the states as some Q1, Q2, doesn't matter, some initial state, right? And then the alphabet of the states are action label pairs. So if our MDP was going from one second. Okay, I'll just write it here. So if our MDP was going to state S0, S1, S2, S3, and so on and so on, by doing action A0, A1, A2, A3, A4, and so on and so on, our alphabet would be A0, L, whatever the F of S0, comma, A0, S1, F of S1. These are our alphabets. Okay. And then, yeah, there's a transition function. And then there are safe states. And these safe states, we want it in such a way that only the states that can be reached by reading a valid trace of the original MDP are the ones that are the final states, that are the safe states. Does that make sense what we want out of the MDP? What we want to do is that we want to weed out all the impossible traces from the MDP. And we want to make a deterministic word automata where the safe states are only the ones that are all the feasible traces of the MDP. So if you reach a safe state, you have reached it through a feasible path. Right? So the states represent the possible set of MDP states. Compatible. Yeah, right. Okay, I guess the example might help. Or yeah, how we reject impossible traces is that phi m only accepts traces that are consistent. So we define this in a way that our delta function in such a way that if q n and then some a naught l naught. So if a naught l naught, if at l naught it does action a naught and reaches a viable state, only then. So then whatever this is q n plus 1, this is also a safe state. That's all I mean. If this is a legal action, then whatever we go to should be a safe state. And then we'll make a set of all the safe states among this huge safety automata that we have. And these set of safe states are the ones that if we reach will be the viable traces that we can get out of our MDP. Is this even a little bit clearer?
I have a question here. So what do you mean by impossible states or impossible traces in an MDP here? So firstly, you're talking about the original MDP without applying
I'm talking about the original MDP. Yeah. So I'm talking about
what
the
do you
original
mean
MDP.
So
So
what do
for
you mean by
example,
impossible?
if it's at S naught and there is no action A4 defined on it, so it can't go from S naught A4, right? So we only care about traces. We only care about traces that are feasible in the original MDP, and we want to design our abstraction in such a way that the safe states in our abstraction are the ones which we reach only by taking the feasible traces of our original MDP.
Okay. And but I mean, often when people define an MDP, this typically all actions are sort of valid in every state. It's just that some of these actions might lead you to a state that is not desirable in the MDP. That is not how you're defining. In your case, the possible number of actions you can do in each state is like certain actions may not be valid from certain states according to your definition.
Yeah.
And okay. Therefore, this concept of feasibility.
No, but this, yeah, I have a kind of a problem with this, because then if usually abstraction allows, it keeps all the feasible states, but a sound over approximation is allows you to include infeasible states. Now you're saying you want to make an abstraction which keeps exactly the same, only the feasible states? What is
No, but are all the states in our abstraction of the MDP will have a lot of infeasible states also. But I'm saying the winning region, the set of final states should only be the ones that are the feasible states.
Yeah, but the final ones have to be.
Yeah, the final ones
In
should only be
between,
the
they
ones.
can violate. So then A until B kind of property, how can you include? I mean, the final state is B.
Like no state in the
Huh?
sorry, no state in this final. There should be no state in this set of final states from which all infinite paths eventually leave F, right? So
Yeah, but they may
yeah,
still reach B, but
wait,
there's a violation along the way.
a violation to what?
A until B. Suppose property.
Yeah,
A.
but we haven't defined the safety property. I'm just abstracting the MDP here.
No, so
on this, I'll even come up with an even smaller set.
Yeah.
After this, I'll come up with an even smaller set, which will be the set of the states that actually care about the violation or not the violation. This is just the states that are even feasible to reach in our MDP, right? Is that like, yeah, after this, now I'll come to a safety property. I haven't even talked about the safety property in this first one.
Yeah, if you restrict yourself to safety property, even then I don't know what you mean by okay.
Okay, maybe. Yeah, we can come back to it, like if it's fine.
Yeah, maybe continue, and I think this will be a bit more clear once you present the whole thing.
Okay, yeah, I'll try to give an overview, and then maybe whatever details I can try to give, I'll try to give. So, like we had that LTL thing for the water tank. So we can always make a bushy automata from any LTL property. So we make a bushy, we make a safety automaton using that LTL property. So for that G, what we had, this is how a safety automata will look, right? For these things. So now we have two automatons. One is the safety automaton and one is the abstract MDP automata. And then what we do is that we construct a safety game, which is a cross product of these two automatons. This is the abstract MDP automata. This is the LTL specification automata. Okay. And then, yeah, we construct a safety game where two players are playing. One is the environment, one is the agent. The environment chooses the labels, the agent chooses the actions, and all the final states here are the ones in which I wanted to know the final states here, the final states in QM were all the feasible states, right? All the states that could be reached in the original one. So here, if the safety specification is on, so if it said, yeah, this state doesn't violate safety specification, comma, this state is reachable. These sort of states, union, this wasn't even a reachable state. So in which we don't care about whether a shield works or doesn't work because the state was not even reachable. Right. So this will be the final states for our safety game.
Can you remind once what is QM and FM here?
Right. Yeah. So QM is the abstract, the states in the abstract MDP. Q is the states in the LTL spec automata, LTL specification automata.
Right.
L are the
FM
labels.
are the final states in the abstract MDP.
Okay, so you're taking a cross product of these things, huh?
Yeah. L are the labels, A are the actions.
Okay.
We had in the, and then I'm saying that now we take a cross product of this. This is generally how cross product is just defined. Right. So when we take a cross product, I'm saying that take all the final states take all the non-final states in QM, which were not even reachable by our original MDP, and take those final states take those states that were reachable by our MDP and are also safety specification says that they are also viable, as in like they are also safe. Right? Does that make sense?
Yeah, that makes sense actually. So just a question in this abstract and automata for the MDP, the initial states are also inside FM, right?
The initial state inside FM. Only then the safety automata can work, right? Because otherwise we'll never leave.
Yeah. So not the safety automata, you mean the abstract automata for the MDP?
So the abstract automata for the ADP.
Yeah. Right? Okay, sure. Yeah, got it.
Okay. Just to make this clear, you're trying to reach to the abstractor set of the LTL specification, right? The automata.
I'm trying to reach what?
The abstractor set, right? Since you said that.
Yes. So I'm trying to reach that subset of the safe states in the MDP that actually satisfy my specification. So I had my MDP, I had my abstract MDP. Now I have my LTL specification MDP. I'm saying these states are the ones that are also achieved by that could also be feasibly achieved by the MDP and are also safe by our LTL property. This is what I'm doing in some sense. And then I'm saying we can also take these random states that were not even achieved by our MDP because we don't care if the shield works on them or not. This is what that is, right?
Yeah, what could that achieve? I mean, why are they doing?
So the paper claims that the abstraction has already failed on this. So these states are not even achieved. So we don't care about these states, whether it's reachable to that state, whether shield works on that state, it doesn't work. We don't care about it. This is the main part that we care about, is the intersection where
I'm also a bit confused about that. I mean, this is if we don't care about it, might as well also leave it outside of FG, right? I mean,
even
it's okay either way, right?
For me to understand, but this is how they plan to proceed, and this is exactly the thing that we cannot. That abstraction is failed, so we no longer require any enforcement of shield on it.
So is there any experimental result? Sorry, you can go on.
No, you go on.
So I was saying, is there any experimental result where they say that without including these random states, they make better progress or better performance?
No, there is no experimental result to that. There is experimental result on how fast the synthesis process is mostly. So okay. Now this was if this is a better visual, we have calculated this, but there are still states here that when reached can go outside, right? We want to remove those states. So that's why we calculate the winning region of this intersection. And this winning region will give us the subset, that subset.
What are the two in this Venn diagram? What is left? What is the left side? What is the right side?
LTL safety automata and the MDP automata, abstract MDP automata. So this intersection basically are those states which are reachable by the MDP and are also safe according to the LTL spec.
Okay. Yeah,
and reachable by the MDP and safe by the LTL specification.
Because it's an abstraction, there could be some things that go out, but they should not be reachable in the original MDP.
Right? They should. So I'm saying that there can be some states that go out. That's why we want to create an even smaller subset of a winning region And within this winning region, like I said before that, I explained that for the winning region, we will always have a strategy to stay in the winning region. We will always have a strategy to stay in the set. Sorry, not in the winning region. We'll always have to strategy to stay in the safe set. If there is a state here which satisfies the LTL spec, no matter what the environment does, we can always go to a different state. We can always take an action.
Yeah, that's okay. But what is the advantage of doing like that? I mean, you're taking the over approximation, which has some unreachable behavior, okay,
Right.
and then you're doing something to restrict. Why? Is there an advantage because you can do the game?
No.
Why did you go put all the unreachable one, then you're restricting? And then presumably the shield is constructed over this abstract.
Over this winning region, yeah. Over this, once you come up with the strategy over the winning region, then shield just takes the strategy and then employs the strategy.
So there's an advantage in doing like that, huh?
Yeah, apparently. So they're saying that W is the core of the states where the safe strategy exists. So yeah, and then this winning region can be computed by a lot of algorithms, like they've mentioned. And then if we wrap our agent in the shield, we only allow the transitions within this W winning region. Then no matter what the environment does, we can never violate the safety specification. Right. Right. Now, since the shield from here, synthesizing is trivial, all it does is that it takes the winning strategy and it only allows those actions that keep the game inside the winning region. So delta S is just it updates the shield exactly as the game would, and then it only allows those actions that would keep.
And the winning region is that intersection, huh?
Not the intersection. It's even a subset of the intersection, which can, from where we have a strategy to stay in the
stay in it.
Region.
Okay.
To stay in it. Right. So at each step, the shield looks ahead one move in the game and returns those actions that are guaranteed safe. So that means they lead to the state from which a safe strategy exists. Right. Yeah. So in this sense, if in the sense of water example, if we talk about, this is the MDP abstraction that they've given, if it's visible. Right. So in this MDP abstraction, so this is, like I said, it should be some action, comma, label. So this is the action, this is the label, this is the action, this is the label. And if we reach Q2, we know that we have taken like some feasible action basically from which we reach Q2. That it was at Q0. If we open it, we can reach Q2 in 2 seconds. If it was open at 2 liters per second. Sorry. Yeah. Then here is the interesting part. So if you see here in Q3 comma QD, sorry, in Q3 comma QD, the system should, so here if it chooses close, right? Here if it chooses close, then here doesn't matter what it chooses, whether it chooses close or open, it will always reach Q fail. So in some sense, the shield needs to look ahead in Q3 comma QD and not choose close and always choose open. And Q3 comma QD is the state in which the level is between 2 and 3. So basically, if it would be that Q fail is not actually reached, and we cannot be sure because we have to consider all evolutions possible. Yeah. Thus, the shield needs to deactivate the closed state in Q3 comma QD. Right. So Q3 comma QD with the close action will not be in our winning region. And Q3 comma QD with open action will be in our winning region, because once we take this action, we'll go out of the. So once we take Q3 comma QD, we'll still stay in the feasible region, comma close, comma C. We'll stay, and then we'll go to Q2 comma Q2 close, and then we'll go to Q1 comma QF close, and from there we'll go to Q fail. Right. So just taking this, our next 3 steps are determined, and we have to go to Q fail. So we should know to look ahead and never take this option, and that's what the calculating the winning region does. Winning region tells us exactly which states will lead us out of the winning region or safe states ultimately. So that's why this works out. Obviously, it's a little tricky to do it, but yeah, I'll show the experiment. So there is this two grid games. There is a 9x9 grid, 15x9 grid, and the objective is visit all colored regions in the correct order. There is some order given to visit it, while avoid walls and any of these bombs, right, or these moving agents you have to avoid, and then avoid staying on a bomb for more than 2 steps. Sorry, avoid walls and moving agents. So you have to avoid walls and then avoid staying on bombs for more than 2 steps. So this 515S1 is used in both of these, while 5S2 is only used in the first one. Right. This is the DFA for both of them. Avoid staying on a bomb and avoid walls and moving objects one. Now they did some testing, and when they used on the 9 grid, they synthesized the shield in about 2 seconds, and on a 15x9 grid, they synthesize the shield, which only uses less constraint, less LTL specification. I guess they did it faster. And they've used post shielding every single time because they really like the rank option, in which agents can rank their things, and then a shield can tell us which is the highest possible rank that doesn't violate. And they've also never used penalty rewards because they have actually figured out that it works better without penalty. So here, 3 without penalty, that is the one that works the best, and the 3 with penalty is the one that actually works the worst. No, the one that works the worst is also without penalty. I don't know how. Okay, they haven't given an intuition for why that is the case, but yeah, 3 for them. The 3 without penalty is the one that's working the most. Penalty, if you remember, is the way we were giving reward in the post one, in which you were saying that every time you take an unsafe action, change it and also give a penalty for choosing it. Yeah. Should I go back to some part that we didn't understand?
Yeah, so I actually wanted to understand the shielding construction a bit. So, firstly, when we get this safety automata from the LTL spec, that has got a booking condition, right? The acceptance condition.
Yeah, booking condition. Yeah.
Okay, and then when you're taking the product here, so when you're taking the product and constructing the safety game,
Right. Yeah.
this F is basically the set of states that you're supposed to visit infinitely often according to the bookie condition, right?
Yes. Perfect.
Yes. So then this FG in the safety game for the safe player to win, they need to visit FG infinitely often for them.
Infinitely many times. Yes.
Okay. And then according to that, you're considering the strategy.
Yeah, and then you calculate the winning region. What are the states that will make us visit this?
Right. So then you some standard fixed point I measure.
Right. Yeah, that's perfect. I forgot to say the inlet in the book.
Okay. Yeah, sure. So, but yeah, so the game has got a bookie sort of winning. Yeah, okay, sure.
Yes. Yeah. Okay. All of them are infinite games. Any reactive game in this way will be an infinite game.
Right. That makes sense. Yeah. Okay. So then, so then I have this question, right? So suppose I have got a safety condition that says that let's say I've got some kind of a system and there's some valve, and the safety condition just says that don't just leave the valve, never leave the valve open, right? So whenever you open the valve, eventually close it, right? Something like that.
Right? Finally close, I guess. Some sort of that.
Or some the automata would look like if you go through a valve open state, then there is a loop around valve open, and then the bookie condition says that you eventually come to a state where the valve has become closed, right? Something like that, maybe.
Right. Yeah.
So what I'm asking is then when we actually make this shield, let's say that when we open the valve, and when we attempt to close it, the environment, there is always a non-zero chance that the valve will remain stuck. right?
Right.
So then in this case, the game is not winnable if you ever open the valve, right?
The game is never winnable if you ever open the valve.
Yeah, because so suppose the valve is initially closed, I can open it, and when I try to open it, when the agent tries to open it, it will open always. But when the agent now tries to close it, maybe the flow is strong or whatever.
There is a chance that it will be always. Yeah.
Correct. So then the game is never winnable. So in this sort of a situation,
here the winning region. There is no winning region also, right?
Right.
Winning region would be something like this.
Region will just be never open the valve. Just never.
Yeah, right. So if there is no winning region in the safety property itself, we can't ever get a winning region in the MDP. So we can never get it right. So we can always have we can always need to have a feasible winning region in the AKL property to even do that.
Right.
I mean, that's what I understand it. That we should.
So,
yeah.
What? No, so basically all I was saying is that sort of a thing. I mean, there, according to this formalism, if the probability of this becoming unsafe is just zero, let's say, or something like that.
Right.
Yeah. That makes sense. Okay. So also this look ahead that we have, right? So the look ahead is actually, I mean, it's kind of we have the perfect amount of look ahead that we would need to always establish safety, right? So let's say that
look ahead is due to the winning region, right? So we look ahead is basically we know which states lead out of the winning region. That's the sort of look ahead we have.
Right.
Yeah.
So suppose if there was basically suppose if there was some kind of a the similar example, but now the environment can't just force you to keep the valve open always. The environment can force you to do it n times, and when the n+1 time it has to let you close the valve, right? So now suddenly this game is actually safe, and the look ahead, if we think in terms of
what is the maximum number of times you can keep the valve open in a straight and then have to close it. That's
that will be captured in the winning region, right?
Yeah.
So the second question I had is, why do you want this kind of an abstraction of the MDP? Because I mean, what I'm saying is, you can always just, instead of having it abstract automatically, you can take the MDP itself and create all these products, right?
So I thought, but I think the reason for that is that MDP can have infinite states, right?
Okay.
So we will always want to come up with finite states, and then the best way to come up with a finite state is to just come up with a automaton that has finite states.
Right.
Even I had the same question, but yeah, this is I think it's the best. Yeah.
But then, I mean, so ultimately, whatever the policy sees, I mean, if you're implementing a policy that is going to be, even if it's some neural network or whatever, like it is only going to see effectively some finite. It is going to have some finite information. Yeah. So that will sort of give you a natural abstraction in this case.
Yeah. So even in the abstraction that I showed you of the water tank, it's not like they reduced the number of states or anything. All they did, they have like 100 states for every single water level.
Correct.
But it's just that. So yeah, abstraction. I don't think we should look at abstraction in the sense like it simplifies something. It just is the perfect way to model the reachable states. That's all it is. If it's infinite, obviously we need to make it finite. But I first looked at in sense of, if there are like, we group the states together. But I feel like that's not maybe the best way of looking at it. The best way of looking at it is whatever gives us the best feasible traces anyway. Even if it's 100 states, 200 states, we don't do that.
Right, I see. So, I mean, I guess one way to think about it is that in the actual MDP in this water tank example, there are infinitely possible water levels. The underlying MDP is infinite. But then maybe the sensor reading the water level only gets an integer value.
Oh, right. Yeah. We can do that. Right. If there is a state which it can overflow. We haven't modeled we haven't written the overflow. Right. Yeah. That is actually good. That is actually good way of thinking about it.
Right. Okay. That makes sense.
Yeah.
Yeah. Let me just look at my notes and or if anybody else has a question, please go ahead. I'll just start it.
Right.
The look ahead. I have a question about the look ahead. I imagine in this game thing, the look ahead, you can do it only if do a finite amount of look ahead, no?
Yes. Yeah.
So will that be enough? I mean, that may restrict the kind of properties. I mean, there must be some restriction on, I mean, if in the look ahead, sometimes you require an indefinite look ahead, those kinds of properties you can't ensure. That restriction is there.
So, I don't think so. So when we say a winning region, the state A is in a winning region, which means that no matter what you do, it can never go out of the winning region. If it's not in a winning region, that means it is currently safe, but after some finite number of steps, by this precise steps, it will go out. So yeah, I think the look ahead is those steps, number of steps after we know that it can go out of the safe state. So I don't know how to have an infinite look ahead. What sort of properties might require an infinite look ahead?
No,
I think-
I can see anything which has like any liveness properties. I mean, A until B. I mean, you can never tell when B occurs. Huh? You can always.
No, I think actually, if you assume that there is a good enough finite abstraction of the MDP, I don't think that a look ahead will be needed. If I'm understanding things correctly, in the sense that suppose if you have even have A until B,
No,
what
but but if there is a finite abstraction for all the properties, then I mean there'll always be some properties for which is true of the order. I mean, might be violating the MDP for which may not be a finite abstraction. I mean, if the property that is possible.
But the way, maybe. But what I'm thinking in terms of is something like this. Let's say that if you have some A until B kind of a condition, right? Now, two things can happen. Let's say that whenever I'm playing A, if it is possible for the environment to prevent me from playing B, right?
Yeah.
If it is always possible for the environment to prevent me from playing B, then the shield will determine that it's, we cannot even, there's no winning conditions. The shield will say that, there's no.
Right. Yeah.
On the other hand, let's say that it is possible for the environment to prevent, it is not possible for the environment to always prevent me from playing B. So the environment will eventually be to some kind of a position where it will be forced to allow me to play B. So then that would be some state in the abstraction of the MDP. And since the abstraction of the MDP is finite, how much time it will take us to get to that state is going to be a finite number of things. So that is the finite look ahead that we would need. That is how I'm understanding this kind of a thing.
So
I think
why I don't understand the infinite look ahead is that if there is a state inside the safe states, how is it possible that it takes infinitely many steps to go out of the state? Like that's not even possible, right? Because if there are only finitely many states inside the winning region, it has to take at least that many. Like it can go through every single one of them, and only then go out of the winning. It can explore all the 2 to the n possibilities and still go out of the winning region.
no, so
Does
that
it
is what the winning condition is, right? So if the winning condition is bookie, what that basically would mean is that if you start from the safe state, you can meander for as long as you like. It's not like you will take infinitely many steps, but you can.
But you need to come back to a safe state infinitely many times. You're right.
But
You're
the
right.
path, the length of the time of the path that you spend outside the safe state is potentially infinite.
Should be finite. No, it should be finite, right? Like if it's a bookie condition, it should be
finite, but it's unbounded, is what I'm saying.
Right. Yeah.
So even if it takes 10,000, whatever, all of those are valid like paths that win eventually, right? But I think what's happening is that the shield, what it will do is it will not even allow you to go outside. It will be like, if you go outside, I don't know if you're going to come back. So I'm not going to allow you to go outside, right?
Because it has already calculated the winning region.
Correct, yeah. Now the only way that the shield might be forced to let you to go outside is if the environment says, no, you need to go outside, right? So let's say the environment is forcing you to go outside. Now the environment can be like, okay, I'll just lock you outside now. So if that is the case, then the shield will calculate that as part of the winning region and give up, saying that, okay, I can't find
Right. Oh, right. Yeah, that's the reason they have. If they go outside abstraction even once, then they're like, okay, fine, we're done. Like, there's no point coming back inside.
Correct. Then basically, I think somewhere in the fixed point computation will reach like an empty state, and then an empty state.
That means that there are some things, they are shielding by restricting too much.
Yeah, restricting. Yeah. And that's why I asked that example, right? So suppose if it's the case, let's say that you have a valve, and so initially it's closed, and then I open it. When I try to open it, it'll always open. But then if I try to close it back again, because of the flow of water, there is, let's say, a 10% chance that it will fail closing, right? Now, that safety probability is that, if I open the valve, it should eventually close. Like, I should eventually close the valve. I should not just leave it running forever. Right? So that's kind of a property, right? So it's like,
open until close.
If has been open until close, something like that, right?
Yes.
So then the region will actually never let me open it, because if I open it, because there's a 10% chance I'll not be able to close. The environment can lock me out. In the sense, the environment can force me to just always fail closing it. So I never end up closing it, and the booking can get violated, and therefore the shield is going to just force me to leave the valve closed, right? But if we think about it, then we should, this is, in this example, that's not perhaps the best thing to do, because I know, yes, I mean, it can happen that the valve just gets stuck open, but the chance of that is going to exponentially reduce with every attempt I make, right? Not that kind of a thing at all. So yeah, in that sense,
I mean, in that way, LTL itself is restrictive, right? Like LTL doesn't give you an idea of.
Yeah. I think there is. I'm vaguely aware of some works out there which have this probabilistic LTL kind of a thing. I mean, there is some logic there which try to come up with a probabilistic LTL logic. I don't know if there is synthesis or like game work around that, but yeah.
Right.
I think this will also hold for CTL also, right?
Yeah, I assume like
all of these steps.
Everything that I mean, sorry, Digant, you aren't audible. Your voice is breaking.
No. I think you go ahead.
Yeah, I assume this is all useful for CTL as well, since like every single property that is true, every single property that I use for LTL here are, you can calculate winning reason, you can make push it on it, everything. So yeah.
Okay, any other questions?
So one thing about this probabilistic thing, the pointed out, like if there's a 90% chance that it may come back, but there's a 10% chance that it will not, and the safety condition is just shutting down the 90% chance for the other 10% chance, and that doesn't seem right?
I mean, it seems right if there's something that will happen and a 10% chance is much more critical as a crash or something like that, right? I feel like it's still right because the sort of safety policies they're talking about as well, like modeling a automated car or something like that. Even not taking a 10% or a 5% risk makes sense. I don't think it's too restrictive in that sense.
But when I tell you where kind of this is a bit weird is that it's not actually the chance of the valve getting stuck open or the safety property being violated, there is actually zero. It can happen, but the probability is zero. Because
right. That's true. Because if you do it infinitely many times, it'll.
Yeah, exactly. Right. So even when it gets stuck at the intersection of all of these.
Diganta, you're not audible.
Yeah.
Sorry, is this better?
Yeah.
Yes, much better.
So I'm saying that the event where the valve gets stuck is kind of the intersection of the valve gets stuck in step 1, in step 2, in step 3, and so on. So that intersection is going to have lower and lower probability. So ultimately the probability is going to be zero. So yeah, I mean, even then you might say that I don't accept a chance of zero probability as well, but it is a zero probability occurrence that something unsafe will happen. So yeah, I mean, I don't know.
No, it won't be zero. I mean, what is the? I mean, it will. What is the chance? Like, let's say 0.1 chance it will fail, and 0.9 it is not. So what is you going to do? So your first 0.9, then first 0.1, then 0.9 into 0.1, and 0.9 square into 0.1. So it's going like that.
So it will be 0.1 and 0.1 square, right? Because first
it'll convert to.
And then it remains stuck and remains stuck, remains stuck and remains stuck and remains stuck. It's like 0.1, 0.1.
No, you'll take the probability where it can get stuck, independent of the path length, right? I mean, of course, I mean, if you doesn't include the path length, then it's 0. But if you take the total probability, then it is not exactly 0.
Is it? But no, but like, why do I need to take that? Why do we
Because
consider the other two cases? Because the event is
because
different.
even if we reach one time, then that is all we need. We need the system to crash, right?
Yeah, right. So, but the system, the system is not going to say, okay, so firstly, the system crash is not something that is an event in our model, distribution at all.
Yeah,
So,
Diganta, once again, you got bad.
am I audible?
Yeah, intermittently.
It's still muffled. It's very muffled.
Let's see. I'm sorry. I think there's some technical issues or something. I don't know what I'm doing about this. Can you hear me?
Yes, yes. Slightly, but yes, you're still.
Maybe I'll just I'll just speak slowly if it works out well. Otherwise, I'll try typing. Let me know if you can't hear me still. So what I'm saying is that even of if it's this situation where there's a crash or there's some explosion or something, it's not even an event in a probability distribution. So a probability distribution is simply over whether the valve gets stuck in the first time or not, right? So the unsafe event for us is that the valve gets stuck forever. That is something we don't even model in some sense, right?
Yeah, that is something we don't. Yeah.
Yeah. So then what is the chance of that happening? That happens if the valve gets stuck in the first situation and second one and third one and so on, right? So that event means that we have to toss every time, and every time we are picking a point one at least, right? So it's not like every time the valve gets
that's
stuck,
what I
it's
was saying
zero.
also.
Yeah.
Yeah, so in every run getting stuck to the bad state is the probability is very 0. But the shielding is actually, I mean, preventing us to take that path altogether, right? If there is a chance to.
Exactly. Yeah.
Yeah.
So that is, I mean, that should not happen, right?
Yeah, maybe. I mean,
should not happen depends on what sort of thing we are modeling, right? Like, we don't know. Maybe Volve it shouldn't happen, but something more critical.
Yeah. I mean, maybe so I'm saying that is 0.1 to 1 call stuff, right?
Yeah,
But
Diganta, I think you're not audible. Okay, so it's very bad. The connection.
But yeah, I also got the idea. I mean, it depends on the perspective. I mean, what is your ultimate goal? That's it.
Okay. Any other questions, comments? Okay, so he does agree to some extent. Okay, so if there are no comments, I'll thank everyone for thank you, Shobit.
Thank you so much.
Yeah.
Thank you for staying, everyone.
Yeah. Be in touch. Yeah. There are three more people who have to two and a half lucky has to finish. I'll announce when they do so and so we'll be in touch. Yeah. Okay.
Thank you so much.
Thanks.